Somewhere about 50 light years from here, there's a planet that spends its entire life screaming around its star. A ball of gas bigger than Jupiter, close enough to its sun that you could not call the distance a gap, so much as a wound. A full year there, one complete orbit, takes a little over 4 days. Sit down to a long weekend, and the planet has already lived and died and lived again. By every rule we had written down, it has no business being there at all. We named it 51 Pegasi b, which is the sort of name you give a thing you did not expect to find. Its star, 51 Pegasi, is quiet and ordinary, a near twin of our own sun, the kind you would pass over on any star chart without a second glance. And welded to the front of it, almost touching, sits a giant world where a giant world should be impossible. Nobody had planned for this. Nobody had even allowed for it. The story starts on a cold night in October 1995 in the south of France, at an observatory called Haute Province. 2 Swiss astronomers, Michel Mayer and his young student Didier Queloz, had spent months watching a single star breathe. Not literally. What they were measuring was the tiniest wobble in the star's light, a shiver so small it barely counted as a measurement at all. Queloz was 29, and he half assumed he had made a mistake. Here is what they were doing, and it is stranger than it sounds. You cannot see a planet next to a star. The star is a floodlight. The planet is a moth. So instead you watch the star for a wobble, a faint tug back and forth, because a planet's gravity pulls on its sun just as the sun pulls on the planet. Queloz was looking for a whisper of movement in the color of the light. He found a shout. Their instrument had a name, Elodie, a spectrograph bolted to a modest telescope that splits starlight into its colors the way a prism does. When a star drifts toward you, its light crowds slightly bluer. When it drifts away, it stretches slightly redder. Mayer had spent years chasing a precision most people thought was pointless. He wanted to measure motion of a few meters per second in a star trillions of miles away. Walking speed across the void. It sounds like madness, and it very nearly was. The wobble came back every 4.2 days. That number should have stopped his heart. A 4-day orbit means the planet is almost grazing the star's surface, roughly 20 times closer than Earth sits to the sun. And the tug was huge, far too big for some little rock. Whatever was pulling on 51 Pegasi had the mass of Jupiter. A Jupiter in a 4-day orbit. It was on paper absurd. Queloz did what any careful person does when the universe hands them something impossible. He assumed he was wrong. He checked the instrument. He checked his math. He worried it was a flaw in the telescope, a trick of the star itself, a bug buried in the software. For months he tried to make the signal go away, and it refused. The planet was simply, stubbornly there. Picture Queloz that summer, a graduate student sitting alone with a curve on a screen that should not curve the way it did. No fireworks, no eureka shouted down a hallway. Just a young man quietly terrified that he was about to either embarrass himself in front of the entire field or rewrite it. For weeks he lived in that narrow space between blunder and revolution. Most of science actually happens there. When he finally showed Mayer the numbers, the older man did not celebrate. He went quiet. They both understood that if this was real, a great deal of what they had been taught was now wrong. They announced it that October at a conference in Florence, in a room full of people who knew exactly how insane it sounded. A giant planet, hugging its star in a place no giant could ever form. To feel why this landed like a slap, you have to know the rule it broke. Giant planets are made of gas, and gas needs cold to gather. Close to a star, it is far too hot. The gas boils away before it can ever pile up into a world. Giants are supposed to be born far out, in the deep freeze, where Jupiter and Saturn live. A gas giant that close to its star was like finding a snowman standing in a furnace. Not everyone believed it. Within days, an American team, led by Jeffrey Marcy and Paul Butler, pointed their own instruments at 51 Pegasi, half expecting to prove the Swiss wrong. Instead, they saw the exact same wobble, right on schedule. That was the moment it stopped being a rumor. The planet was real, and so was the problem. It had just dropped on the entire science of how worlds are made. Before that October, the hunt for other worlds was a career you did not admit to at parties. Astronomers who chased exoplanets were treated a little like people who chased ghosts, earnest, faintly embarrassing, forever pursuing something that refused to appear. Claims had come and gone for decades, and most had collapsed the moment anyone looked closely. Mayer and Kulo were working a field with a long reputation for breaking hearts, which is exactly why they checked and checked and checked again. They started calling these things hot Jupiters, which is astronomer humor for a nightmare. A hot Jupiter is a gas giant boiled to well past 1,000 degrees, so close to its star that its atmosphere swells up and streams away like steam off a kettle. 51 Pegasi b was the first one we ever saw. It would not be the last. In the years to come, we would find them everywhere, and every single one was a fresh insult to the rulebook. Try to actually stand on the day side of 51 Pegasi b, and of course you cannot, because there is no ground and you would be vapor in an instant. The temperature runs well past 1,000 degrees Celsius, hot enough to glow a dull, sullen red. Its star fills a third of the sky, an unblinking wall of fire that never sets, because the planet almost certainly keeps one face turned toward it forever. One side, endless day, the other, a strange and lesser hell. Think about what actually happened here. For all of human history, we had exactly one solar system to study, our own, and we quietly assumed it was the template for everything. One night in France, two men looked at one ordinary star and found out the template was a lie. Everything we believed about how worlds are built had just been contradicted by the very first example we ever found beyond our own front yard. That is not a small thing to carry home from work. It took the world a while to grasp the size of it. 24 years later, in 2019, Mayer and Kulo were handed the Nobel Prize in Physics for that one wobble. By then, the discovery had grown into an entire branch of science with thousands of worlds in its ledgers. But in 1995, all they had was a number that would not go away, and the slow, cold understanding that the galaxy had never agreed to our rules. I find something almost funny about it, in a dark way. We spent centuries building a beautiful, orderly theory of how planets come to be, and we were rather pleased with ourselves. Then the universe waited until we had the right instrument, leaned in close, and showed us a world that made a mockery of the whole thing. Not out of malice. It simply never agreed to our rules in the first place. We just never thought to ask. And here is the part that should unsettle you. 51 Pegasi b was not some lonely freak we could file away and forget. It was the first crack in a dam. Behind it stood thousands of worlds we had not yet met, each one stranger than the last, and the water was already beginning to seep through. Before we drown in that flood, though, we owe ourselves one honest look backward at the story we had been telling ourselves about how a world is supposed to be born. What if everything you believe about how a world is born is really just a story, and you believe it for one reason only? You have only ever watched it happen once. For most of human history, we had a single solar system to study, our own, and from that one example, we built a law for the entire universe. It felt like knowledge. It was closer to a guess wearing a very good suit. And for 200 years, almost nobody thought to doubt it. Look at the standard picture of our solar system, the one printed in every school book. The sun in the middle, calm and gold. The planets strung around it in tidy rings, moving like the gears of a great clock. Small rocky worlds gathered close to the warmth. Enormous gas giants holding court far out in the cold. Everything spaced, ordered, lawful. It is a deeply comforting image, and that was part of the problem. The idea is older than you might think. In 1755, a young Immanuel Kant, better remembered for philosophy than physics, suggested the planets had condensed out of a vast rotating cloud of gas and dust. 40 years later, the French mathematician Pierre-Simon Laplace reached nearly the same picture, more rigorously, and lent it his considerable authority. They called it the nebular hypothesis, a cloud collapsing, spinning itself into worlds. It was elegant, and it was mostly right. Here is the mechanism, and it truly is beautiful. A cloud of gas and dust, light years across, drifts through space until something nudges it, and gravity begins to pull it inward. As it falls, it spins faster, the way a skater pulls in her arms, and it flattens into a disk. At the center, the pressure lights a fire, and a new star is born. Around it, in a leftover disk, the scraps begin to clump. Dust finds dust. Worlds start to gather. Now comes the rule that mattered most. The 151 Pegasi B would later shatter. Close to the newborn star, it is scorching, hot enough that only metal and rock can stay solid, while everything lighter is cooked into vapor and blown away. Across a certain distance, though, and the temperature falls past freezing. Astronomers call it the frost line. Beyond it, ice survives and gas can gather in enormous amounts. Inside the line, you build small rocky worlds. Outside it, you build giants. So the theory made a clean, confident promise about where things belong. Rock close in, gas far out. Little worlds near the fire, huge worlds in the dark. Mercury, Venus, Earth, and Mars, modest balls of stone, huddled near the sun, Jupiter, and Saturn, vast and frozen, banished to the outer dark where they were free to swell without limit. A place for everything, and everything in its place. The universe, we assumed, agreed with us. And why wouldn't we believe it? The theory explained our own solar system almost perfectly. It got the order right. It got the sizes roughly right. It explained why the planets all orbit in the same direction, in nearly the same flat plane as though stamped from a single spinning disk. When a theory tidily accounts for every fact you own, it is dangerously easy to forget that you only own one set of facts. That is a trap. We walk straight into it. Walk the solar system outward, and the logic seems undeniable. Mercury, a scorched cinder. Venus, a rock choking under its own cloud. Earth, blue and improbable. Mars, a rusted desert. Then a gap, and the giants begin. Jupiter, a striped colossus you could pour more than 1,000 Earths into. Saturn with its rings. The pale ice giants beyond. Small things near the fire, great things in the freeze, exactly as ordered. It looked less like coincidence and more like a law. There were other clues that seemed to seal it. Nearly every planet spins the same way the sun does. They all travel their orbits in the same direction, like runners on a shared track. Their paths are almost circular and almost flat, all lying within a few degrees of one another. That is not what chaos produces. That is the fingerprint of a single spinning disk that made all of them at once. From where we stood, the evidence looked overwhelming. By the 20th century, the nebular model had hardened into something close to scripture. It filled the textbooks. It shaped how we imagined every star we saw, each one presumably ringed by its own quiet, orderly family of worlds, sorted rock inside and gas outside. We stopped calling it theory. We called it the way solar systems are. And a thing you no longer question is a thing that can wound you. The dream underneath, it was older still. For centuries ago, a defrocked friar named Giordano Bruno stared into the night and declared that the stars were other suns, each with its own worlds, perhaps its own life. The church burned him alive for that, along with several other heresies, in a Roman square in the year 1600. Bruno had no proof. He simply could not accept that we were the only story in the sky. It would take us 400 years to learn how right and how wrong he was. But strip away the elegance, and one flaw sat at the dead center of everything. Our entire law of planet formation rested on a sample size of one. One star, one family of worlds. We had raised a cathedral of confidence on a single data point, and then forgotten the point was single. Any honest scientist will tell you a sample of one is not data. It is an anecdote. We had mistaken our anecdote for the mind of the universe. This is the quiet arrogance at the heart of the whole story, and it is a deeply human one. We saw what was near us and called it normal. We saw what was familiar and called it universal. It is the same instinct that once put our planet at the center of creation and our species at the top of it. Every time, the correction has been humbling. We just kept assuming the next one would somehow spare us. To be fair, a handful of people had wondered. In the 1600s, the Dutch astronomer Christian Huygens speculated about planets around other stars and even the beings who might walk them. Isaac Newton mused that the fixed stars were simply distant suns. But wondering is cheap, and proof was impossible with the tools of the age. So the speculation stayed speculation, a pleasant thing to imagine on a clear night, while the neat blueprint of our own system quietly calcified into certainty. So by the early 1990s, this is exactly where we stood. Ask any astronomer what other solar systems looked like, and they would have described ours. Rocky worlds near the star, gas giants far away, on slow, circular, well-behaved orbits. Not because anyone had ever seen such a system, because it was the only kind the theory permitted. The whole field was waiting patiently to have its beautiful expectation confirmed by the sky. And that is what makes what came next so brutal. The very first planet we found around a normal star was not a distant, dignified giant on a wide circular path. It was 51 Pegasi b, a Jupiter crushed against its sun in a 4-day orbit, precisely the thing the theory swore could not exist. The universe did not gently revise our blueprint. It took its first swing directly at the part we were proudest of. I keep returning to that confidence, because it is the real subject of this chapter, not the physics, the certainty. For 2 centuries we looked at one example and mistook it for the rule of all creation, and we taught that mistake to our children as settled fact. There's a lesson buried in that, and it is not a flattering one. The universe is under no obligation to resemble the small corner of it that happened to make us. But 51 Pegasi b, for all the damage it did, was not even the first blow. Here is the detail we skipped, the one that still puts a chill in me. 3 years before that night in France, we had already found planets somewhere far more forbidden than any furnace. Not around a living, sunlit star at all. Around a corpse. Around the spinning, radioactive remnant of a star that had already died in fire. And those, by any honest reckoning, were the first worlds we ever found. 2,300 light years from here, in the direction of the constellation Virgo, there is a small dead thing spinning in the dark, and it is not alone. Around it move at least 3 worlds, patient and silent, circling a star that already died. Its sun went off like a bomb a very long time ago. What is left is a cinder the size of a city, turning 160 times every second, drenching those worlds in radiation that would kill you before you finished reading this. And these, of all the planets in the sky, were the first we ever found. To understand where we are, you have to understand what killed the star. When a star far heavier than our sun runs out of fuel, it does not fade quietly. It collapses in on itself in less than a second and rebounds as a supernova, an explosion so violent it briefly outshines an entire galaxy of 100 billion stars. What remains at the center is crushed almost out of existence. A neutron star, the corpse. A neutron star is matter squeezed past all reason. Take something heavier than our entire sun and crush it into a ball you could drive across in a few minutes, maybe 12 miles wide. It is so dense that a single teaspoon of it would weigh about 1 billion tons here on Earth. Its gravity is so fierce it visibly bends the starlight passing behind it. This is not really a place. It is a wound in space where a star used to be. Some of these corpses spin, and spin fast, firing beams of radio energy out of their magnetic poles. As a beam sweeps past the Earth, we catch a pulse, then nothing, then a pulse again, like a lighthouse glimpsed across a black sea. We call them pulsars, and here is the strange gift they give us. Those pulses arrive with the steadiness of the finest clock ever built, so regular you can time them for years without a single beat slipping out of place. Which is exactly why, in the early 1990s, a Polish astronomer named Alexander Wolzin was listening to one. He was using the Great Dish at Arecibo in Puerto Rico, a radio telescope slung across a jungle sinkhole, tracking a pulsar with the tongue-twisting name PSR B1257 plus 12. He expected metronome perfection. What he got instead was a clock that could not quite keep time. The pulses were arriving a little early, then a little late in a slow, repeating rhythm. A clock that speeds up and slows down is telling you that something is moving it. The pulsar was being tugged, gently, first toward us and then away, over and over. Something was pulling on the corpse. And when Wolzin worked through the arithmetic of that tug, the answer was almost obscene, given where he was looking. Planets. Not one, at least two, and soon a third, orbiting the dead star with the eerie precision of a thing that had been there a very long time. The precision here is almost hard to fathom. A pulsar like this beats over 100 times a second, and by stacking millions of those beats, you can time its rotation to within a fraction of a millionth of a second. That is what let Wolzin feel the pull of a world twice the mass of our own moon from 2,000 light-years away. He was weighing something he could never see by the faint stutter it put into the ticking of a dead star. It remains one of the most delicate measurements our species has ever managed. The numbers were startlingly exact, sharper than anything we would manage for 51 Pegasi 3 years later. Two of the worlds weighed around 4 times the mass of Earth, rocky things, roughly the size of super-Earths. A third was a mere sliver, about twice the mass of our moon, one of the smallest worlds we have ever detected anywhere. 3 planets, tracing calm circles around a monster. It was, frankly, hard to believe. Astronomers labeled them with the dull poetry of catalogs, the pulsar, and then letters for its worlds. The smallest, the one barely heavier than our moon, is so slight that detecting it at all was a minor miracle. Sit with that for a moment. Before we had confirmed a single planet around a normal star, we had already weighed a world smaller than most people would guess is even possible, orbiting the least hospitable object imaginable. We ran before we could walk, and we did it in a graveyard. Extraordinary claims have a way of dying young, and Wolzin knew it. So he brought in a radio astronomer named Dale Frail to nail it down, testing the signal against every other explanation the two of them could invent. The pattern held. In 1992, they published quietly and carefully, and the verdict stood. Humanity had found its first planets beyond the sun, and they were circling a corpse. Now sit with how wrong this is. A furnace, a hot Jupiter, is at least orbiting a living star. These worlds orbit the aftermath of an apocalypse. The supernova that forged this pulsar should have vaporized or flung away anything nearby. Any planets the star owned in life should have been annihilated in its death. And yet here were 3, calmly orbiting the grave. Either they survived the unsurvivable, or, stranger still, they were born out of it. Born out of it is the answer most astronomers now favor, and it is genuinely unsettling. The explosion, or the shredding of a companion star, could have left behind a disk of debris circling the fresh corpse. And from that ring of ruin, out of the ashes of a dead sun, new worlds could slowly gather. These are not survivors of the old system. They are a second generation, children assembled out of the wreckage their dying star left behind. Do not imagine anywhere you could ever stand. These worlds are scoured endlessly by the pulsar's beams and the howling wind of particles pouring off it. Any atmosphere will be stripped to the bone. The ground, if there is ground, would glow faintly under a bombardment of radiation no living cell could survive. There is no warmth here, no light you could call daylight, only the merciless flicker of a spinning corpse. They are worlds in every technical sense, and graveyards in every other. Here is the detail I cannot get out of my head. The first planets humanity ever found, the very first worlds we ever confirmed beyond our own sun, were not gentle blue marbles. They were not distant twins of Earth. They were irradiated rocks orbiting the radioactive ember of a star that had already exploded. Our opening act in the search for other worlds was to walk straight into a tomb, and most people have never even heard of it. That is partly why 51 Pegasi B stole the glory 3 years later. A pulsar planet felt like a ghost story, a freak of the graveyard, too strange to count as a beginning. A giant around an ordinary sun like star felt like us, like a door swinging open on a world we might one day recognize. So the history books tend to start in 1995 in France and quietly skip the tomb we found in 1992. I think that is a mistake. The tomb told us something the furnace did not. What it told us was this: the universe does not build worlds only in the warm, tidy nurseries of our textbooks. It builds them in the dark. It builds them in the aftermath of catastrophe, out of poison and ruin, in places our theories had marked as strictly forbidden. The very first data point we ever collected beyond our solar system was already screaming that our rules were far too small. We simply were not ready to listen yet. There is a kind of awful poetry to it, and I would be lying if I said it did not move me. Somewhere out there, 3 worlds are circling the thing that killed everything it once had, worlds made from the corpse of their own creator, keeping perfect time in the dark for no one at all to see. We like to think of planets as beginnings. Cradles. These are the opposite of a cradle, and they were the first ones the galaxy chose to show us. So within 3 years, we had 2 impossible facts sitting side by side. Worlds around a corpse where nothing should survive, and a giant welded to a living star where nothing should form. The pulsar we could almost wave away as a freak of the tomb. The hot Jupiter we cannot, because if a giant planet cannot be built where we keep finding it, then there's only one way it got there. Something reached across the dark and dragged it over enormous distances out of the cold and into the fire. And whatever stood in its path did not survive. Picture a planet the size of Jupiter, born far out in the cold, where giants are supposed to be born. Now picture it moving, not orbiting, moving inward, spiraling toward its star across millions of miles and millions of years, slow as grief and utterly unstoppable. Everything smaller in its way is either swallowed or hurled into the dark. This is the only way we can explain the hot Jupiters. And once you accept it, the tidy nursery of our textbooks becomes something much worse. Remember the wall we hit. A gas giant cannot form pressed against its star. It is far too hot there for gas to ever gather. So a hot Jupiter must have been built somewhere out in the cold, past the frost line, where Jupiter itself was made. Which leaves one enormous question standing in the room. How did a world that formed in the deep freeze end up welded to the furnace? It did not teleport. It traveled. To see how, go back to the disk, that flat ring of gas and dust circling every newborn star. A young giant does not sit quietly inside it. Its gravity carves ripples through the gas, waves that pile up ahead of it and trail behind it. And those waves pull back on the planet like a headwind. Slowly, relentlessly, they bleed away its energy. And a planet that loses energy does the one thing you would least want it to do. It falls inward. So the giant begins to spiral toward its sun, shedding orbit after orbit, sinking through the disk like a stone through thick water. There is nothing dramatic about it, no single catastrophe, just an endless, patient descent over hundreds of thousands of years. Some of these worlds fall all the way in and are eaten by their star, gone without a trace. Others stop just short, parked at the very lip of the fire, and those are the hot Jupiters we still see today. The bones of the idea were actually older than the crisis it solved. As far back as 1980, theorists like Peter Goldreich and Scott Tremaine had worked out how a planet and its disk tug on each other. When 51 Pegasi B landed in 1995, an astrophysicist named Douglas Lynn and his colleagues reached for that math almost at once, and within months had shown how a giant could migrate inward and survive as a hot Jupiter. The tool to explain the impossible had been sitting in the drawer the whole time. We had simply never needed it before. Now, think about what that journey does to everything else. A young solar system is not empty. Between the giant and the star, smaller worlds are forming rocky bodies, the embryos of planets, all of it directly in the giant's path. As it plows inward, it shoves them, scatters them, flings them into the star or out into the void. It is less a graceful migration than a bulldozer crossing a nursery. Whatever was there first rarely lives to tell about it. This forces a complete reimagining of how these places begin. We had pictured the birth of a solar system as serene, a slow gathering of worlds into their proper orbits, calm and lawful from the very start. The migration story tells a different one. It says the early years are chaos. Worlds shove past worlds. Giants wander. Orbits are made and unmade. What settles out at the end, if anything settles at all, is only whatever managed to survive the demolition. For a while, this was just theory, a clever escape hatch invented to spare us from the impossible. Then the evidence piled up. We found hot Jupiters everywhere, and many of them on orbits tilted at wild angles to their star spin, exactly what you would expect from worlds that were shoved around rather than born in place. We found young stars with gaps and spirals gouged into their disks, the very scars a migrating giant should leave. The story stopped being a rescue and became a description. And here is where it stops being someone else's problem. There is strong evidence that our own Jupiter did exactly this early on. In a model called the Grand Tack, the young Jupiter migrated inward toward the Sun, roughly to where Mars now orbits, dragging chaos behind it. Then, caught in a gravitational dance with Saturn, it turned and migrated back out again, like a ship tacking against the wind. Our largest planet did not stay where it was born. It roamed. If that model is right, Jupiter's wandering shaped everything we are. On its way in, it may have swept up and scattered much of the material that would have built the inner planets, which could be why Mars is such a runt, far smaller than it has any right to be. It stirred the leftover rubble into the asteroid belt. It may have flung water-rich bodies inward, seeding the young Earth with some of the oceans you owe your life to. A giant went for a walk, and here you are. Let that settle for a second, because it changes the mood of everything. The comfortable, orderly solar system from the last chapter, the one we held up as the universal blueprint, may itself be the calm after a storm. Not a pristine clockwork that was always this tidy, but the wreckage that happened to stabilize. Even home, it turns out, carries the scars of an early war. We just lived too briefly and arrived far too late to smell the smoke. Migration through the disk is only one way worlds move. There is a rougher way, and it happens after the gas is gone. Planets that stray too close to one another trade gravitational shoves like billiard balls on a cosmic table. One world gets flung inward onto a tight, scorching orbit. Another gets kicked outward or onto a wildly stretched, eccentric path. Whole architectures are rearranged in a handful of violent encounters. Some hot Jupiters may have arrived not by sinking, but by being thrown. And the losers of those encounters meet a colder fate. When a giant slingshots a smaller world hard enough, that world can be thrown clean out of the system, cut loose from its star forever. It does not fall into the fire. It falls into the dark, alone, and it keeps falling. We will return to those exiles later in this story, because there may be far more of them than anyone is comfortable admitting. For now, just hold the image. A war has losers, and space is where they are buried. Even the giants themselves were not spared the chaos. In another well-tested model, the outer planets of our own system began far closer together, then hundreds of millions of years later tumbled into instability. Neptune and Uranus shifted and migrated outward. Countless icy bodies were scattered, some raining down on the inner worlds in a long bombardment that battered the young moon. Our solar system did not gently mature. It convulsed more than once before it finally grew quiet. So here is the reframe this chapter leaves you holding, and it is not a gentle one. A planetary system is not a clock that was wound once and left to tick in peace. It is a survivor, It is what remains after a long and violent contest, after migrations and collisions and near misses and worlds thrown screaming into the void. The orbits we admire are not a plan. They are a truce. And a truce, by definition, is only what is left when the fighting stops. I used to find the solar system comforting, a still and stately thing. I do not anymore, not since I understood this. Every quiet orbit is the final resting place of something that fought its way there or was pushed. The peace is real, but it is late, and it was bought at a price. We grew up inside the aftermath and mistook it for the whole story. The same mistake we made with the blueprint, the same mistake we keep making. The universe is rarely as calm as it looks from safe distance. For the search itself, this changed everything we expected to find. If worlds wander, if systems tear themselves apart and reassemble, then there is no reason on Earth to expect other stars to resemble ours. We should expect giants pressed and close, worlds on tilted, stretched backward orbits, systems crammed tight, systems blown wide open, and everything in between. The galaxy, if migration was right, should be a vast museum of survivors, each one shaped by its own private catastrophe. There was only one problem with all of this, and it was a large one. By the early 2000s, we had a scant few dozen of these strange worlds, each one wrung out of the sky one painstaking wobble at a time. It was enough to know the rules were broken. It was nowhere near enough to know how badly. To answer that, someone would have to count the planets, not by the dozen, but by the thousand. So we built a machine to stare, without blinking, at a single patch of sky for 4 straight years. And what it saw is still hard to believe. For 4 years, a small telescope drifting behind the Earth did nothing but stare. One patch of sky, up near the constellations Cygnus and Lyra, about 150,000 stars, watched without pause, without blinking, waiting for them to flicker. Not to brighten, to dim, ever so slightly, as though something had passed in front. Every flicker was a world crossing the face of its sun. And when the count came in, the worlds did not arrive by the dozen. They arrived by the thousand. The trick is almost childishly simple, which is exactly what makes it beautiful. When a planet passes directly between us and its star, it blocks a thin sliver of the light, and for a few hours the star looks a hair dimmer. Wait, and it happens again, on a perfect schedule, once every orbit. Measure how much the light drops, and you learn the planet's size. Measure how often it drops, and you learn the length of its year. Shadows on a wall, read like a book. But understand how faint these shadows are. When the Earth crosses the sun, seen from far away, it blots out less than 1/100th of 1% of the light. That is, the flicker Kepler was built to catch, a dimming so slight, it is like watching a single moth drift across a stadium floodlight from the far side of the city. To see it, you need a detector of almost absurd sensitivity and a patience no human eye could ever hold. So we built a machine that felt neither boredom nor doubt. To do it, Kepler carried the largest camera ever flown into space at the time, 95 million pixels drinking in the light of that one crowded field. Every half hour, it recorded the exact brightness of 150,000 stars at once. And it did this for years without complaint. The data poured back to Earth in a flood no person could ever read by eye. It took banks of computers and small armies of astronomers just to notice the shadows hiding in the noise. The man who dreamed it up spent most of his career being told no. William Barucki, an engineer at NASA, had been arguing since the 1980s that you could find planets this way, by their shadows. He was turned down again and again. The proposals rejected, the technology called impossible, the whole idea judged a touch eccentric. For 20 years, he refined it and resubmitted it and watched it get shelved. Most people would have quit. Barucki simply kept coming back. The doubts were not unreasonable. To catch the shadow of an Earth, you had to measure starlight steadier than anyone ever had, from thousands of stars at once, continuously, for years on end. A single glitch, a wobble in the pointing, a flaw in the detector, and the whole delicate signal would drown in noise. NASA hesitated for good reason. But Barucki had run the tests, quietly, stubbornly, proving the thing could actually work. In the end, they gave the persistent man his telescope. Kepler left the Earth in March of 2009 and settled into an orbit trailing our planet around the Sun, so nothing would ever block its view. Then it turned its single, unblinking eye toward that one rich field of stars and locked on. It would not look away for years. No sweeping the sky, no chasing targets, just one long, obsessive stare into the same crowd of distant suns, waiting for the faintest of shadows to fall. It did not take long for the flicker to start coming back. First a handful of clean detections, giants mostly, easy shadows. Then smaller ones, and smaller still, as the team learned to trust the data. Within a couple of years, the candidate list had swollen past 1,000. Then 2,000. Then more. Every dip was another world nobody had ever known was there, and they were piling up faster than anyone could confirm them one by one. Then came the number that reorders your sense of the universe. When astronomers accounted for all the planets Kepler must have missed, the ones tilted wrong to ever cross their star from our angle, the arithmetic pointed at a staggering conclusion. On average, essentially every star in the galaxy hosts at least one planet. There are more planets out there than there are stars in the sky. Hundreds of billions of them in our galaxy alone. Worlds are not rare. Worlds are the most common thing there is. But it was the kind of worlds that unsettled us most. The single most common type of planet Kepler found is something our own solar system does not contain at all. Bigger than Earth, smaller than Neptune. A broad family we call super-Earths and mini-Neptunes. They're everywhere out there, the default world, the galaxy's favorite design. And we do not own a single one. The most ordinary planet in the universe is a kind we have never once seen up close, because there simply isn't one at home. Some of what it found looked less like a solar system and more like a magic trick. Take Kepler 11, a star ringed by at least 5 planets all packed inside an orbit tighter than Mercury's. A whole crowded family squeezed into a space where we keep only scorched rock. They move in a delicate gravitational lockstep, so close together that a sky watcher on one would see the others loom as disks, not points of light. Nothing in our neighborhood ever grows that intimate. Out there it is routine. Others read like something out of a story we thought we had invented. Kepler 16b is a world that orbits not one star but 2, a pair of suns circling each other while the planet loops around them both. Stand on it, and you would watch a double sunset, 2 shadows stretching away from your feet, exactly the image a science fiction film once sold us as pure fantasy. We found it in the real sky. The galaxy, it turns out, had beaten our imaginations there by a long way. Scroll the full catalog, and a strange loneliness sets in. Lava worlds, puffed up giants, worlds packed in tight, worlds circling 2 suns, worlds nothing like anything we had names for. What you almost never find anywhere in those thousands is a system that looks like ours. Small rocks in, big giants out, wide and calm and orderly. We had gone looking for our own reflection in the galaxy, and the galaxy kept handing back the faces of strangers. And buried in that flood were the ones that made people fall silent. Now, and then Kepler caught a world close to the size of Earth, sitting at just the right distance from its star for liquid water to survive, neither boiled nor frozen. Kepler 1 86f, Kepler 4 52b. Worlds we could not visit, could not photograph, could do nothing with except know that they were there. Small, temperate, possibly wet, orbiting stars whose light left them before any of us were born. We could not tell if anyone was home. We still cannot. Kepler's watch did not end gracefully. In 2013, the second of its steadying wheels gave out, and the telescope could no longer hold its rock-steady stare. The great vigil was over. But the engineers coaxed years more out of it, balancing the crippled craft against the faint pressure of sunlight itself, and it kept finding worlds until the fuel finally ran dry in 2018. By then it had confirmed thousands, with thousands more still waiting in the data. One machine, one patch of sky, an entire new science. Think about the scale of what one stubborn idea achieved. Before Kepler, we had a few hundred known worlds, scraped out of the dark one at a time, over 15 years. After Kepler, we had thousands and a firm statistical grip on the billions we would never see. It turned exoplanets from a collection of oddities into a population, a census, a map of how the galaxy actually builds worlds. And the map looked nothing at all like the one we had drawn for ourselves. I try sometimes to hold the real number in my head, and I cannot quite do it. Look up on a clear night at a few thousand stars. Now understand that essentially every one of them has worlds, and most stars you cannot even see have them too, and the total climbs into the hundreds of billions in this one galaxy, among hundreds of billions of galaxies. The sky is not sprinkled with worlds. It is drowning in them, and that fact, strangely, makes the dark feel lonelier, not less. So now we have our census and our vertigo and one uncomfortable truth pressing in from every direction. The galaxy is stuffed with worlds, and almost none of them are anything like home. It is time to stop counting them from a distance and start walking among them, one by one, to meet the menagerie. And the first monster in the collection is a world with no ground at all, only a planet-wide ocean of molten rock, glowing, churning, with no shore you could ever hope to reach. Try to imagine a world where the ground is not a place you can stand, but a thing that flows. No continents, no shore, no solid rock anywhere at all, only a planet-wide ocean of liquid stone, glowing a dull, furious orange, churning under a sky that never cools. The tides in that ocean are not made of water. They are molten rock, rising and falling to the pull of a star that hangs enormous and motionless overhead. This is a real place. We have measured it. It has a name. We call it 55 Cancri E, and it circles a star you can actually see. On a clear, dark night, in the constellation Cancer, there's a faint point of light about 40 light years away, an ordinary yellow, star not so different from our own Sunday. You could pick it out with binoculars. Around it whips this scorched, swollen world, roughly twice the size of Earth and 8 times its mass, a super-Earth in the most hostile meaning of the word. The first thing that should alarm you is the year. One full orbit of 55 Cancri, it takes about 18 hours. Not 18 days, 18 hours. It sits so close to its star that a birthday there comes and goes faster than a single one of ours. To keep from falling in, it must move at a speed that would carry it from the Earth to the Moon in under an hour. It is not so much orbiting its sun as skimming the surface of it. We know it in more detail than almost any world its size because it does something rare. From our angle, 55 Cancri E crosses the face of its star, so we catch both its shadow and the wobble it raises, and from those two clues we can weigh it and measure it once. That combination gave us its density, and its density told us something was off. It is a rocky world, yes, but a deeply strange one, denser and hotter and weirder than any rock has a right to be. At that distance, a world cannot spin freely. The star's gravity has seized it and held it fast, so that one hemisphere faces the fire forever while the other stares eternally away. There is no sunrise on 55 Cancri E. There is no day and night, no turning of the sky. Just one face pinned in permanent, blistering noon, and one face locked in a strange, starless dark. Two halves of the same world, enduring two entirely different hells. On the side that faces the star, the temperature climbs to somewhere near 2,400 degrees Celsius. That is hotter than the melting point of iron, hotter than the melting point of the very rock the planet is built from. So the rock does not stay rock. The entire day side is thought to be molten, a hemisphere of magma stretching from horizon to horizon, seething beneath a star that swallows a quarter of the sky. There is no ground to reach because the ground has become a sea. Picture standing at the edge of that sea, if there were an edge, and if you could exist there at all. Beneath you, an ocean of liquid rock glowing from within, red where it is cooler, white where it burns hottest, its surface crawling with slow currents miles across. No waves like ours, no wind you would recognize, just the endless churn of molten stone under a sky the color of a blast furnace. It is beautiful in the way a thing that would kill you instantly can be beautiful. For a while, we told ourselves a far more romantic story about this world. In 2012, a team, led by the astronomer Niku Midhusudhan, announced something extraordinary. The data seemed to say that 55 Cancri was unusually rich in carbon, and if you squeeze carbon hard enough, deep inside a planet, it does something remarkable. It crystallizes. The suggestion was that a third of this world might be made of diamond, a planet with a heart of jewels. You can imagine how that traveled. A diamond planet, worth some absurd invented number of dollars, raced around the world in a single day. It was the good kind of impossible, the kind that makes you smile rather than shiver. For a brief moment, 55 Cancri, it was the most glamorous world in the sky, a gem the size of 2 Earths, catching the light out there in the dark. It was a lovely idea. It did not survive contact with better data. As astronomers pinned down the star more carefully, the carbon story weakened. The ratios shifted. The diamond interior, once the headline, shrank to just one possibility among several, and a fading one at that. What replaced it was less precious and far more menacing. Not a jewel, a furnace. Not a heart of diamond, but a face of magma, and a chemistry that turned every romantic notion we had into something closer to a warning. Here is what the newer observations point toward, and it is genuinely strange. On a world where the surface itself is vaporized rock, the atmosphere may be made of the very same stuff, silicate vapor, the gaseous ghost of stone. And where there is vapor, there can be cloud, and where there is cloud, there can be rain. On the cooler edges of 55 Cancri, it may quite literally rain rock, droplets of molten mineral condensing out of the sky and falling back into the sea that made them. The world refuses to sit still even for our instruments. Over the years, its brightness has flickered and shifted in ways nobody fully understands, as though the dayside were partly veiling and unveiling itself, clouding over and then clearing. Some think enormous plumes of vapor rise and fall. Some think the lava ocean itself churns and cools and reforms. Whatever is happening, it is happening on a scale we can detect across 40 light years, which means it is happening on a scale beyond anything in human experience. More recently, the James Webb Space Telescope turned its eye on it and found hints that 55 Cancri may hold onto a real atmosphere after all, thick with carbon gases, somehow surviving right on the doorstep of a star that should have stripped it bare ages ago. That should not be easy. A world that close should have had its air boiled off and blown away. That it may still be wrapped in a shroud of gas, refreshed perhaps by the magma sea below, only deepens the mystery of how such a place holds together at all. And then there's the side we can barely see, the face turned forever from the star. It should be cooler, but by how much nobody is sure. If there is any atmosphere to carry the heat around, winds of vaporized rock might blow from the burning day into the dark, dragging warmth across the terminator, that thin permanent line of dusk between the two worlds. Somewhere along that line, molten rock might harden into the only solid ground the planet has, a shore of freezing stone between an ocean of fire and a night that never ends. There is no version of a human moment here, and that is rather the point. You could not land. You could not stand. You would not survive long enough to register the heat before you became part of the vapor in the sky. Everything soft about you, everything that makes you a person, would be gone in less than a heartbeat. This is a world with no room in it for anything like us, and it is one of the more common kinds of world in the entire galaxy. That is what stays with me about 55 Cancri. We went looking for other Earths, other cradles, and one of the first monsters the galaxy handed us was a world made entirely of the thing we are most afraid of. Fire with no edge, heat with no mercy, a whole planet that is nothing but the inside of a volcano turned out and hung in space. We even try to dress it up as a diamond. The universe was never going to be that kind. And there's a quieter reason this world should hold your attention. 4.5 billion years ago, the earth beneath your feet looked something like this. Newly formed, bombarded, glowing, its surface a global ocean of magma under a sky raining fire. Every rock you have ever touched, every mountain, every grain of sand was once liquid like the dayside of 55 Cancri. We are not simply looking at an alien impossibility. We are looking at our own infancy, frozen in another star's light, a hell we happen to crawl out of. So the first monster in the menagerie is fire without a shore. But the galaxy is not satisfied with oceans of lava. On some of these scorched worlds, it really does rain, in the way we mean the word, drops falling out of clouds. Only the drops are not water. On one of them, the rain is molten iron, condensing on the frozen night side and falling in a metal storm. On another, the rain is glass, hurled sideways by winds faster than a bullet. We are about to walk straight into the weather. On a world about 640 light years away, in the faint constellation of Pisces, evening arrives with a change in the weather. As the burning day gives way to the endless night, the temperature drops just enough for the air to let go of what it has been carrying. And it begins to rain. Not water, iron, droplets of molten metal, falling through a scalding sky. A storm of liquid iron sweeping across a world where nothing has ever been alive. The planet is called WASP-76b, and it belongs to a breed we have come to know and dread, the ultra-hot Jupiters. It is a gas giant, larger than Jupiter itself, but bloated and puffed by heat, orbiting so close to its star that a year there lasts under 2 of our days. Like so many of these worlds, it is tidally locked, one face held forever in the glare, one face forever turned away. And between those two faces, the metal weather is born. The name is a small joke of acronyms. WASP stands for the Wide-Angle Search for Planets, a set of humble little cameras in the Canary Islands in South Africa that watch huge swaths of sky for the telltale flicker of a transiting world. It has found hundreds of them. WASP-76b was just another entry in the catalog, another hot Jupiter among many, until someone looked closely at its light and realized this particular giant was raining metal. The extraordinary out here hides inside the routine. Start on the day side, the hemisphere that never stops staring at the star. The heat there is monstrous, climbing well past 2,400 degrees Celsius. And at those temperatures, the ordinary rules of matter come apart. Metals we think of as the very definition of solid do not merely melt. They boil. Iron itself turns to vapor and rises into the atmosphere. So the dayside air hangs thick with the gas of a metal we build our machines out of. The sky is full of iron. But no world can hold that heat all on one side without trying to spread it. Ferocious winds tear from the blazing dayside toward the cooler night, moving thousands of miles an hour, dragging the vaporized iron along with them. They howl across the terminator, that permanent border between fire and dark, carrying their cargo of metal gas into the shadow. And in the shadow, for the first time, the temperature begins to fall. Just enough to change everything. On the night side, the air cools toward a mere 1,500 degrees, and that difference is the trigger. Iron vapor, carried out of the day, can no longer stay a gas in the colder dark. So it does what water does in our own gentle sky. It condenses, it gathers into droplets, and it falls, a rain of liquid iron pouring out of the clouds of an alien night, sweeping endlessly across the evening face of a world that has never known a single drop of water. We did not guess this from theory alone. In 2020, a team, led by the astronomer David Ehrenreich, using a razor-sharp instrument called Espresso on the Very Large Telescope in Chile, watched the light of WASP-76b as it crossed its star. They saw the fingerprint of iron vapor on the evening side of the planet, and then, on the morning side, they saw it vanish. The iron was leaving the sky between dusk and dawn. It was raining out overnight, exactly as the metal storm demanded. Stand there, in a fantasy where you somehow could, on the evening edge of WASP 76b. Overhead, a sky glowing dull red, streaked with cloud. Around you, wind screaming past at the speed of a hurricane many times over. And falling all around, catching what little light there is drops of molten iron, hot enough to glow, spattering against ground you cannot even see. It is a thunderstorm out of a nightmare, a downpour of the same metal that runs in your own blood, on a world that would vaporize you before the first drop ever landed. Iron is only one flavor of impossible weather. Come closer to home, about 65 light years out in a small constellation called Vulpecula, and you find a world that from a distance would actually look inviting. A deep, rich cobalt blue, the blue of a clear ocean or a summer sky. If you saw it hanging in space, you might, for one foolish second, think of Earth. That would be the most dangerous mistake you ever made. The planet is HD 189733b, and in 2013, it earned a strange distinction. Using the Hubble Space Telescope, astronomers measured its true color, the first time we had ever determined the actual color of a world beyond our solar system. They watched the planet slip behind its star and saw the combined light go very slightly less blue, which meant the blue had been coming from the planet itself. It really is that color. A blue marble 65 light years away, and utterly, lethally wrong. On Earth, the blue is water and air. On HD 189733b, the blue is something far crueler. Its atmosphere is thought to be laced with tiny particles of silicate, the raw material of glass, hanging in the searing sky. Those particles scatter blue light, the way our own air does, which is why the world glows that beautiful color. But it means the clouds themselves are not water vapor at all. They're made of glass. High, drifting, shimmering clouds of tiny glass grains wrapped around furnace. And this world does not hold its glass gently. HD 189733b is another tidally locked giant, roasted on one side, and to balance the heat, it whips up winds of a violence that beggars belief. We estimate them at up to 5,000 miles an hour, 7 times the speed of sound, blowing not up and down, but sideways, screaming around the entire planet. Whatever glass forms in that atmosphere is not falling as a gentle rain. It is being fired horizontally, a permanent sandblast of molten silicate at the speed of a bullet. So take the pretty picture and turn it inside out. That lovely blue is a haze of glass. That gentle-sounding weather is a sideways hurricane of razor grains, moving fast enough to strip flesh from bone in an instant, in air hot enough to melt lead. The most beautiful color we have ever seen on another world is the signature of one of the most hostile places we have ever found. Beauty and horror in this galaxy are very often the same measurement read from different distances. As if the weather were not enough, the star is slowly killing the planet. HD 189733b orbits so close that its atmosphere is heated, swollen, and bled away into space, streaming off the top of the world under its star's relentless glare. And when the star throws off a flare, we have watched the planet's air balloon and evaporate faster still, as though the whole world were being gently, endlessly boiled. The blue is not only violent, it is temporary. This is a planet with a wound that will never close. This is the real horror of these worlds, and it creeps up on you through the vocabulary. Zen, wind, clouds, weather. These are the softest, most domestic words we own, words for a walk with an umbrella, for a lazy afternoon indoors. And the galaxy has taken every one of them and turned it into an instrument of annihilation. Rain that is molten iron. Wind that is a sideways storm of glass. On these planets, the weather report is a death sentence written in words a child would recognize. I think that is why these two worlds unsettle me more than the plain lava planets do. A lake of fire is at least honest about what it is. But a blue marble in the dark, with rain and clouds and weather, it wears the costume of home. It looks like somewhere you could belong, right up until it kills you in a way you have no word for. The galaxy does not seem cruel, exactly, but it has a genius for dressing the unbearable in something familiar. For all that, these worlds are gifts to science, and I do not want to undersell it. Because they're so extreme, and because they are tidally locked, they let us study whether physics push to the absolute limit, how heat moves, how atmospheres circulate, how a planet survives a fire on one side and a freezer on the other. Every iron storm and glass gale we decode teaches us something about air and heat that our own mild sky would never give up. Monsters, it turns out, make excellent teachers. But even iron rain and glass winds are not the end of the heat. We keep climbing the ladder of temperature, world by world, and there's a rung above this one that should not be possible at all. Because there's a planet out there so blistering that it does not merely glow. It burns as bright and hot as a small star, hot enough to tear its own metals apart, hot enough that its sun is peeling it away into a long, luminous tail. A planet sitting right at the edge of no longer being a planet. There's a planet where the word planet begins to lose its meaning. It glows, not with reflected light, the way our worlds shine by borrowing from the sun, but with its own heat pouring out of it, a sullen, furious light all its own. If you could hang it in our sky, it would burn like an ember the size of a world. By temperature alone, it outshines some genuine stars, and its own sun is slowly tearing it to pieces. It is called KLT9b, and it holds a record nobody wants. The day side of this world reaches around 4,300 degrees Celsius. Take that in. That is not lava hot or metal boiling hot. That is closing on half the temperature of the surface of our own sun, on a thing we still, technically, call a planet. It is the hottest planet we have ever found, and it sits so far beyond the others that it feels like a different category of object altogether. For years, there had been an unspoken ceiling in our minds, a temperature past, which we assumed no planet could exist, because surely a world that hot would come apart or simply evaporate away. KLT9b sailed straight through that ceiling as if it were not there. When the discovery was announced in 2017, it did not just set a new record. It forced astronomers to admit they had been quietly wrong about where the edge even was. The galaxy keeps finding our ceilings and treating them as floors. To feel how absurd that number is, compare it to the stars themselves. The most common stars in the galaxy, the small red dwarfs, glow at their surface at around 3,000 degrees. KLT9b, a planet, is over 1,000 degrees hotter than that. If you lined it up against a crowd of real, fusion-powered stars, it would outshine a great many of them by heat alone. We have found a planet hotter than a sun, or rather, the galaxy built one and let us stumble across it. The reason it burns so hot is the monster it orbits. KLT9 is no mild yellow star like ours. It is a brute, a blue-white sun more than twice the mass of the sun and vastly more luminous, so hot at its surface that it pours out a savage flood of ultraviolet light. Most planets never have to survive a star like this. KLT9b orbits it in a day and a half, close enough to feel the full fury of that radiation without a moment's pause. That ultraviolet torrent is the real weapon. It is the same kind of radiation that burns your skin in an afternoon, except here it arrives with a violence no sunscreen was ever imagined to stop, hammering the planet's upper atmosphere without rest. It heats the outer layers of the world until they swell and strain against the planet's own gravity. The air does not merely get hot. It gets so hot that it begins trying to leave. At 4,000 degrees, chemistry, as we know, simply gives up. Molecules, the pairings of atoms that make up water and air and everything familiar, cannot hold together in that heat. They are torn apart the instant they form. So the atmosphere of KLT9b is not built of compounds, but of bare, dissociated atoms, a glowing fog of individual elements too hot to ever combine. On the day side, the very idea of a molecule is a luxury the temperature will not allow. And in that glowing atomic fog, we have found the heavy metals. Using the light filtering through its atmosphere, astronomers have detected iron and titanium in the air of KLT9b, not as dust, not as rock, but as vapor boiled clean off the planet and hanging in the sky as gas. Think about what that means. The metals that would form the bones of a rocky world here drift freely through the atmosphere, cooked into vapor by a heat that treats iron the way our own world treats water. Now, put the pieces together, the swelling air and the boiling metal and the relentless ultraviolet, and you arrive at the most haunting detail of all. KLT9b is evaporating. The star is heating its atmosphere past the point of no return, and the outer layers are streaming away into space, dragged off the planet and blown out behind it. The world trails a long, luminous tail of its own vaporized substance, like a comet the size of a giant planet, slowly bleeding itself into the dark. It is not even allowed to keep its shape. So close to that massive star, the gravity pulling on the near side of the planet is far stronger than on the far side, and the difference stretches the whole world out of round. KLT9b is not a sphere. It is distorted, drawn into something more like an egg, its star-facing bulge straining toward the fire. A planet stretched, boiled, and peeled all at once, held together only barely against the forces working to pull it apart. For all its extremity, it was found by something almost comically modest. KLT stands for the Kilo Degree Extremely Little Telescope, and the name is not false advertising. These are small, cheap lenses, hardly bigger than a good camera, watching bright stars for the faint dip of a passing world. In 2017, they caught the shadow of KLT9b crossing its brilliant sun. The most hellish planet we know was discovered by one of the least impressive telescopes in the business. There is a lesson buried in that somewhere. So we are left with a genuine puzzle of definitions. Here is an object that glows with its own light, radiates more heat than some true stars, and pours energy into space from a body larger than Jupiter. By those measures, it sounds like a star. And yet it is not one, and the difference is everything. Because deep in its core, nothing is burning. There is no fusion, no nuclear fire lighting it from within. All that heat is borrowed, poured in from outside by the star it orbits. That is the line in the end between a planet and a star. Not size, not heat, fire. A real star holds enough mass to crush its own core until hydrogen fuses and it lights itself, a furnace running on its own account. Below that threshold, you get failed stars, the brown dwarfs, and below them, planets warmed only by whatever their sun or their own slow cooling can provide. KLT9b glows like a star and is nothing of the kind. It is a planet wearing a star's clothes. And it cannot last. A world that is boiling away, losing its atmosphere to space, is a world on a clock. It's brilliant. Massive star is also short-lived, fated to swell, and change long before a mild star like ours ever would. Between the evaporation and the star's own violent future, KLT9b is not a stable, ancient world quietly circling forever. It is a brief, extravagant catastrophe, burning fast and bright, already in the process of coming undone. Try one final time to imagine standing beneath that sky, and fail as you must. The star would not be a disk but a wall, blue, white, and blinding, its ultraviolet glare enough to sterilize a world. The air itself would glow around you, hot enough to reduce you to your constituent atoms in the time it takes to blink. And above, streaming off into the black, the ghostly tale of the planet's own substance, lost to space forever. It is a place designed by no one, for no one, at the far edge of what heat can do. There's a word for this, and it is not a comfortable one. Sublime. Not sublime as in lovely, but sublime in the old, dangerous sense. The feeling you get standing at the foot of something so vast and so indifferent that it makes your own existence feel like a rounding error. KLT9b is sublime. It is magnificent, and it is monstrous, and it does not know you exist. and somehow it makes the fire feel almost holy, right at the moment it becomes unbearable. So we have climbed the ladder of fire about as far as it goes. From lava seas, to rain of iron, to winds of glass, to a world hotter than a star, peeling apart in its own light. There is nowhere hotter to go. Push a planet past this, and it stops being a planet, boiled away or swallowed whole. The heat has run out of room, which means the next turn in this story cannot be toward more fire. It has to be toward the dark. And the dark, when we finally turned to it, gave us something that unsettled me more than any furnace ever had. After all these worlds that scream and glow and burn, the most disturbing planet we found was one that did the exact opposite. It gave nothing back. A world drowned in an ink so total, so complete, that it swallows almost every ray of light that touches it, reflecting back less than 1%. A planet blacker than coal, hiding in plain sight beside its star. We had feared the fire. It turned out the dark was worse. Somewhere in the constellation Draco, about 750 light years away, there is a planet that does something no planet should be able to do. It hides, not behind anything. It hides by being dark, so dark that light which strikes it does not come back. Point a beam at it, and the beam is simply gone, drunk down into a surface that reflects less than 1% of what falls on it. It is a gas giant the size of Jupiter, and it is very nearly invisible. It is the blackest world we have ever found. We call it Trace 2b, and on paper it should not frighten anyone at all. It is a hot Jupiter, one more gas giant welded close to its star, circling in about 2.5 days, the sort of world we have met a dozen times already in this story. But this one carries a secret in its skin. Of all the sunlight that pours onto it, hour after hour, year after year, it throws almost none of it back. The rest, it keeps. Trace 2b was not even discovered as a curiosity. When the Transatlantic Exoplanet Survey first caught it in 2006, it looked like an ordinary hot Jupiter, one more giant in a growing pile. Nobody suspected a thing. It took years and the patient eye of Kepler before we realized this particular planet had a property no one had thought to look for. The darkness was hiding in the data the whole time, waiting for an instrument sensitive enough to notice how little ever came back. Let me try to give you a feel for how dark that is, because the number alone slides right off the mind. Fresh asphalt reflects far more light than this. Coal reflects more. Black acrylic paint, the flat, matte kind that seems to eat the light in a room, reflects more than Trace 2b does. This planet is darker than the darkest thing you have ever held in your hand. If you stood beside it, it would not look like a world. It would look like a hole cut out of the stars. And here is the first strange thing, the detail that turns curiosity into unease. This pitch-black world is not cold. It is not some frozen cinder drifting in the deep. It is a hot Jupiter roasting beside its star, its day side glowing at over 1,000 degrees. So it is not truly perfectly black. It smolders faintly with its own heat, a dull and sullen red, like a coal at the bottom of a dying fire. A thing that swallows light and burns at the very same time. We only know how dark it is because of an accident of geography. Trace 2b happens to lie within the very patch of sky that Kepler spent 4 years staring at. So Kepler watched it, orbit after orbit, and measured the faintest rise and fall in the system's light as the planet swung around, showing us first its lit face, then its dark one. That gentle ripple told us how much light the planet was reflecting. The answer, when it finally came, was almost nothing at all. So why does it drink the light? The honest answer is that we are not entirely sure, but we hold a strong suspicion. A cool gas giant can be wrapped in bright clouds, ammonia and water ices that bounce light cheerfully back into space. Trace 2b is far too hot for clouds like that. Instead, its atmosphere is thought to be laced with chemicals that are very good at one thing, absorbing light, and very bad at reflecting it. It is not that the light escapes and dims. It is that the light goes in and never leaves. The likely culprit's red like a chemist's warning label. Vaporized sodium and potassium, hanging in the hot air, soaking up light across a broad range of colors. Gaseous titanium oxide, a fierce absorber, painting the sky black from the inside. There may be other, stranger compounds we have not yet named, brewed in that heat. Whatever the exact recipe, the result is an atmosphere that behaves like a trap for photons, letting them in and refusing almost entirely to let them back out. So picture it, as well as a mind can. A vast dark sphere, larger than Jupiter, hanging close beside its star. On the side facing that star, a deep, ominous glow, not bright, not cheerful, just a faint red heat of something enormous and furious barely showing through the black. No liam, no hailot, no reflected sunlight dancing on cloud tops. Only that low, smoldering ember light, and beyond the terminator, a darkness so complete it is indistinguishable from empty space itself. Sink down into that atmosphere, in imagination, and the light would fade fast. Near the cloud tops, a murky red twilight, the star reduced to a smeared glow through the absorbing haze. Deeper, the darkness thickens until you can not tell up from down, only feel the pressure rising and the heat climbing past 1,000 degrees. There would be no shadows because there would be no light to cast them, only a hot black, crushing nothing, going down and down toward a core we'll never see. It is claustrophobia with the size of a giant planet. There is something about that image that gets under the skin in a way the fire never did. The lava worlds and the iron rain, for all their horror, are at least loud. They rage. They announce themselves. Trace 2b does the opposite. It is quiet. It is still. It absorbs everything and returns nothing. And a thing that gives nothing back is, in some deep and animal way, more disturbing than a thing that screams. We are wired to fear the dark. This is a whole planet made of it. That is really why this world sits where it does in the story. For 8 chapters, we have been afraid of heat, of worlds that burn and boil and glow. And your body understands heat. It knows exactly what to do with fire, which is to run. But darkness is a different kind of fear, older and colder, the fear of the thing you cannot see, the fear of not knowing what is there. Trace 2b marks the turn from the terror of fire to the terror of the dark. And the dark, from here on, only deepens. There is a quiet irony in its other name. Because it fell inside Kepler's field, Trace 2b is also cataloged as Kepler 1b, the very first planet on the list of that great world hunting mission. The first entry in the catalog of a telescope built to find new Earths turned out to be the darkest planet in the sky. Of all the worlds Kepler could have numbered 1, the galaxy handed it a black hole of a planet. I choose to find that funny. It is easier than the alternative. Detecting a world this dark is a special kind of challenge, and it flips our usual methods on their head. Normally, a planet betrays itself by the light it reflects or the shadow it casts. But a world that reflects nothing offers almost no glimmer to find. Trace 2b shows itself to us mostly through its own faint heat and the shadow it throws crossing its star. If it were drifting alone in space, with no sun behind it to be silhouetted against, it would be one of the hardest things in the entire universe to see it all. I keep coming back to that phrase, gives nothing back. There's a loneliness to it the burning worlds never had. A furnace at least shares its fire, floods the space around it with light and heat, insists on being noticed. This planet takes. It absorbs the light of its star and the gaze of our telescopes and returns almost none of either, keeping whatever it swallows sealed inside. In a galaxy full of worlds that shout, we found one that only listens. And somehow that is worse. For the science, darkness is not a dead end, but a clue. How much light a world reflects, its albedo, is a window into what its atmosphere is made of, how hot it runs, what chemistry churns in its clouds. A planet as extreme as Trace 2b marks one hard boundary of what is possible, the very floor of reflectivity, and every world we measure against it teaches us to read the light and the darkness of far more distant places. Even a hole in the sky has something to tell us. And it is not entirely alone in its gloom. As we have measured more of these close and giants, we have learned that many hot Jupiters are surprisingly dark, far dimmer than the bright, cheerful worlds of our own outer system. The heat robs them of their reflective clouds and leaves them somber and dull. Trace 2b is only the extreme end of a whole shadowed population, the darkest of a dark crowd. The galaxy, it seems, keeps more of these brooding worlds than luminous ones. So we have found a world too dark to see. But the galaxy is not finished playing with the raw properties of matter, the things we thought were fixed and settled. Because if a planet can be blacker than we believe possible, it can also be lighter than we believe possible. Out there are worlds as wide as Jupiter, and yet so impossibly, ludicrously light that you could imagine them floating on water, worlds with the density of nothing at all. We have questioned how a planet burns and how it hides. Next, we have a question what a planet is even made of. Here is a thought experiment that sounds like a joke until you realize it is real. Imagine a planet nearly as wide as Jupiter, a giant by any measure, a world you could pour 1,000 Earths into. Now, imagine it is so light, so wispy, so lacking in substance, that if you could find an ocean big enough, it would float. Not sink, float, like a cork, like a bubble on a pond. There are worlds out there with the density of cotton candy, and nobody is entirely sure how they hold together. To understand why that is so strange, think for a moment about density, which is just how much stuff is packed into a given space. A rock is dense. A cloud is not. Our own Jupiter, for all its bulk, is mostly compressed gas, and even it is denser than water. The Earth beneath you is denser still, 5.5 times the density of water, a ball of rock and metal. Density is one of the most basic facts a planet has, and these worlds break it. We call them the super puffs, a rare case of astronomers naming something honestly. Their densities run absurdly low, a fraction of the density of water, in some cases lighter than styrofoam, lighter than cork. A world the size of a giant, weighing as little as a handful of Earths. If you could scoop up a bucket of one, it would feel like scooping up almost nothing at all, a bucket of faintly resisting air. These are planets that are mostly not there. The finest examples circle a young star called Kepler-51, about 2,500 light-years away. 3 planets, all roughly the size of Jupiter or Saturn, yet all together weighing only a few times the Earth. Their density is close to that of cotton candy, the sponge sugar from Fairground, the stuff that dissolves to nothing on your tongue. 3 cotton candy giants orbiting quietly in a row. When astronomers first pinned down the numbers, they assumed they had made a mistake. They had not. So how does a world get that puffy? The leading idea is that these are young planets with modest rocky cores wrapped in enormous, bloated atmospheres of hydrogen and helium, envelopes swollen far out from the planet, inflated and held up by the heat of their own youth. The core might be only a few times the mass of Earth, but the atmosphere around it billows out to the size of Jupiter, thin and vast, like a small stone wrapped in an enormous balloon. Most of the planet, by volume, is very nearly vacuum. But that raises a problem that keeps some astronomers up at night. An atmosphere that thin and that far out should not be safe. It sits high above the planet, only weakly held, right where the star's radiation can seize it. By rights, it should be boiling away into space, streaming off the top of the world, deflating the whole balloon. And yet there they are, 3 of them, puffed up and holding together. Either we caught them at a fleeting moment, or something about how they hold on is still hiding from us. The likeliest answer is that we are watching something temporary, a phase rather than a fate. The Kepler-51 planets are young, only a few 100 million years old, practically newborn as worlds go. Their puffiness may be a stage of infancy, a bloat that time and starlight will slowly bleed away. Give them a few billion years, and they may shrink, deflate, and settle into smaller, denser, far more ordinary worlds. We may simply have arrived early enough to catch the balloon before it lost its air. Or the puffiness might be partly an illusion, which is its own kind of wonderful. Some astronomers have suggested that a planet wrapped in a broad system of rings, seen nearly edge-on, could block extra starlight and masquerade as a much larger, puffier world than it truly is. If that is what is happening at Kepler-51, then some of these cotton candy giants might actually be ordinary planets wearing enormous halos of ice and dust. We're not yet sure which answer is right. Both, frankly, are strange enough. Whatever the exact cause, one thing is certain about a superpuff. There is nowhere to stand. Descend into one, and you would simply keep falling, the wispy outer air slowly thickening around you, the pressure rising by slow degrees, with no surface ever rising up to meet your feet. There is no line where atmosphere becomes ground, no shore, no floor, only a gradual, endless deepening into denser and denser gas. A world with no solid place in it at all, from the outermost haze to the buried, secret core. So matter can be too dark, and matter can be too light. It can also, it turns out, be made of the wrong things entirely. Every world in our solar system was built from roughly the same pantry, rich in oxygen, with silicon and iron making rock and metal, and water making ice and sea. But that recipe is not the only one the galaxy cooks from. Change the ingredients even a little, and you can build a planet out of chemistry our own system never once touched. In 2005, an astronomer named Mark Kuchner sketched out one such possibility, the carbon planet. Around a star, or in a region unusually rich in carbon compared to oxygen, worlds would form from a different set of building blocks. Instead of silicate rock and water, they would be assembled from carbon in its many forms. It was a hypothesis, a what-if, born from the simple fact that not every corner of the galaxy shares our particular chemical luck, and the worlds it predicted would be genuinely alien. Try to picture standing on one. Beneath your feet, not rock, but something stranger, a crust of graphite and dark carbides, black and faintly greasy. Deeper down, under crushing pressure, the carbon would compress into the hardest substance we know. A mantle of diamond, layer upon layer, miles thick, buried in the dark interior of the world. Not a jewel you could ever hold, but a planet with bones of diamond, hidden forever beneath a skin of tar and soot. Beautiful in theory, utterly foreign in fact. The surface of such a world would be a chemist's fever dream. The atmosphere might hang thick with carbon monoxide and methane. Seas, if there were seas, could be made of tar and liquid hydrocarbons, black lakes of the very stuff we pump out of the ground and burn. Clouds of soot, skies the color of smoke. Everything we associate with life on Earth is built on carbon, and yet a world made mostly of carbon would be one of the least welcoming places imaginable. The same element, turned monstrous by sheer abundance. And there's a third way from matter to turn strange, and this one is quieter, almost gentle. Some worlds may be made largely of water, whole planets that are one deep, globe-spanning ocean hundreds of miles down, with no land anywhere and no seafloor you would recognize. These are the ocean worlds, and there may be a great many of them. On the face of it, water sounds like home. But go deep enough, and the water stops behaving the way any water you have ever known behaves. Because under enough pressure, water does something that offends common sense. It freezes solid even while it's scalding hot. Miles down in an ocean world, the pressure grows so immense that water is crushed into exotic forms of ice. Ice that can exist at hundreds of degrees, hot enough to boil at the surface, but locked rigid in the deep. So the floor of such an ocean would be a shell of burning ice, a thing our everyday words cannot even hold. Warm and solid and frozen all at once. Step back and look at what this whole chapter is really telling you. We began this journey worried that planets could sit in the wrong places or spin the wrong way or run too hot or too cold. That was the easy part. It turns out the raw matter of a world, its density, its ingredients, the behavior of its most basic substances refuses to obey the rules we drew from home. Too light to sink, too dark to see, built of diamond or tar or ice that burns. The stuff of planets is stranger than the planets themselves. I find these worlds harder to hold in the mind than any furnace, and I think it is because there is nothing to grab onto. A lava world is horrifying, but you understand it. A planet with the density of a cloud, or an ocean floored with hot ice, slips out of your intuition entirely. It is not frightening the way fire is frightening. It is uncanny, wrong in a way you feel before you can explain it, like a familiar word repeated until it stops meaning anything. The galaxy is not merely violent. It is deeply, quietly weird. So here we are, halfway through the menagerie, dizzy with impossible worlds. Giants in the wrong place. Planets around corpses. Oceans of fire. Rain of iron. Worlds too dark, too light, too strange to be believed. And through all of it, a question has been quietly building at the back of the room, waiting for us to be ready to hear it. We have spent 10 chapters asking why these worlds exist. But the census is in now, and it points somewhere we never expected. Because the strangest system in all of it, the real anomaly, might not be any of them. It might be ours. For 10 chapters, we have been the ones holding the clipboard, cataloging the freaks, quietly tooting at the impossible worlds the galaxy kept handing us. Now the census is complete, thousands of planetary systems weighed and measured, and it is time to see where our own solar system falls on the chart. This is the moment the whole story turns around. Because when the numbers come back, the strangest system in the sample, the one that does not fit, the genuine anomaly, is not any of the monsters. It is the quiet, orderly one we live in. Let me remind you what an ordinary planetary system looks like, now that we have seen so many. It is crowded. It has a big planet close to the star, often a giant, sometimes a hot Jupiter. It is packed with worlds bigger than Earth and smaller than Neptune, jammed into tight orbits near the fire. Its planets often ride on stretched, eccentric paths. That is the common design, repeated across the galaxy again and again. And it looks nothing at all like home. Start with the obvious. We have no hot Jupiter. Our giant sits far out in the cold where the old theory said a giant belongs 11 years to a single orbit, exactly where it should be. For most of this story, that felt like the normal case, and the hot Jupiters the freaks. But hot Jupiters, or at least giants shoved in close, are common out there. The fact that ours stayed home, that no giant came barreling into our inner system, is already a little unusual. Now the strange one. The single most common type of planet in the entire galaxy, the design the universe seems to love above all others, is the super-Earth, that world bigger than ours but smaller than Neptune. They are everywhere. Most stars have one or several. They're the default outcome of building a planetary system. And in our solar system, there is not a single one. Between the Earth and the ice giant Neptune, in the size range the galaxy favors most, we have absolutely nothing. Sit with that absence because it is genuinely bizarre. Earth is the largest of the little rocky worlds. The next planet up in size, Neptune, is nearly 4 times wider and 17 times heavier. In between lies a vast gulf, and that gulf is precisely where most of the galaxy's planets live. It is as if you surveyed every home on Earth, found that the most common house by far is a modest 2-story family house, and then discovered your own street had somehow skipped that size entirely. The most popular kind of world, and we do not own one. Then there is the shape of the whole thing. Our system is spread out, spacious, almost stately. Mercury huddles close, yes, but beyond it the planets march outward with room to breathe, all the way to the frozen edge. Compare that to the compact systems we keep finding, where 5 or 6 or 7 planets are crammed inside an orbit tighter than Mercury's, elbow to elbow around the fire. Those crowded systems are common. Our wide, uncluttered layout is the exception, not the rule. Look closer and it gets stranger still. The planets of our solar system travel on orbits that are very nearly circular, smooth and calm, barely straying from a perfect ring. Out in the galaxy, that is not the norm. Many worlds ride on stretched, eccentric, oval paths, swinging close to their star and then far away, the fossil signatures of past violence and scattering. Our planets, by contrast, glide along as if nothing bad ever happened to them, which, given everything we have learned, is deeply suspicious. The pattern keeps repeating no matter which feature you check. Crowded systems are common. Ours is roomy. Giants pushed in close are common. Ours are held far out. Stretched orbits are common. Ours are round. Super-Earths are common. We have none. On feature after feature, our solar system lands not in the fat middle of the distribution, but out at the quiet, lonely edge. We're not a typical example of how the galaxy builds worlds. We are an outlier on almost every axis at once. When astronomers try to put a number on it, the estimates vary, but they point the same way. Depending on how you count, only a small fraction of planetary systems look broadly like ours, some studies suggesting well under 10%, a few suggesting far less. The precise figure is still argued over. The direction is not. Whatever the exact odds, an arrangement like our solar system, calm and wide and missing the galaxy's favorite planet, is uncommon. We are, statistically, one of the strange ones. So why are we like this? The leading suspect is the giant in our own backyard, Jupiter. Remember the grand tack, that early migration when Jupiter wandered in toward the sun and then retreated. On its way, it may have done us an enormous favor. It could have swept up, scattered, or blocked the material that would otherwise have built super-Earths in our inner system and stopped any giant from settling in close. Jupiter, in this telling, is the reason our inner system is so empty and so calm. Think of Jupiter as a bouncer standing at the edge of the inner solar system. Its immense gravity governs what gets in and what gets thrown out. It may have flung would-be super-Earths into the sun or out into the dark before they could ever grow. It shields the inner worlds to a degree from comets and stray bodies. Whether by luck or by the particular way our system happened to settle, that giant carved the emptiness around us. And in that emptiness, for small rocky worlds were left in peace. And this is where the whole story turns inside out. For 10 chapters, the question was, why do these impossible worlds exist? Why the fire, the iron rain, the darkness, the cotton candy giants? But those worlds, we now understand, are the common outcomes. They are what the galaxy usually makes. The real question, the one that should keep you awake, is the opposite. Not why do they exist? Why do we? What went right or went strange that left us here in this uncommonly quiet corner, on this uncommonly calm little world? It is tempting to leap straight to comfort here, to say our strangeness is exactly what made us possible, that we are rare because rarity is required for life. And there may be something to that. A calm, wide system, a stable circular orbit, a giant to guard the gate, may indeed be part of why the Earth stayed habitable long enough for anything to think about it. But be careful. We do not actually know that yet. We are one example, again, drawing grand conclusions from a sample of one, again. Still, the possibility hangs there, and it is a heavy one. If systems like ours are rare, and if life needs a system like ours, then the two facts fold together into something lonely. It would mean that the very features that make us an anomaly are the same features that keep us alive. That we exist precisely because we are strange. And that most of the galaxy, built the common way, may be the wrong kind of strange for anything to ever wake up inside it. There is a particular vertigo in this chapter that I want to name honestly. All through this story, you have been able to keep the monsters at a distance. Out there, other, not us. This is the moment that comfort is taken away. We spent so long marveling at how weird the galaxy was. And the whole time the galaxy was looking back and thinking exactly the same thing about us. We are the specimen now. We are the world that does not fit the pattern. It is a strange thing to learn about your own home. I owe you some honesty about the limits here, because good stories can outrun their evidence. Some of our apparent strangeness is a trick of how we hunt. Big planets close to their stars are the easiest to find, so of course our catalog is stuffed with them, and smaller, wider worlds like ours are simply harder to see and surely undercounted. But the missing super-Earth is not that kind of illusion. Those we could detect, and around our own sun, in that favored size, there is genuinely nothing. That silence is real. So the mirror has turned, and it will not turn back. For the rest of this story, every impossible world we meet carries a second meaning. It is no longer just a monster in a distant cabinet. It is a measure of how far from the ordinary our own gentle home really is. The dread that has been building through 10 chapters has quietly changed direction. It used to point outward at them. Now it points inward at us, and at the fragile, improbable arrangement that lets us exist at all. But we are not done with the violence yet, and I do not want you getting too comfortable in this new unease. Because before we can truly understand how rare our calm is, we have to look at the opposite of calm. We have to walk through the wreckage. Out there are worlds that orbit their stars the wrong way, backwards, against the grain, as though something vast once reached in and shattered the order of things. These are not merely strange planets. They're crime scenes, and every tilted orbit is a fossil of a catastrophe. Every planet in our solar system orbits the sun in the same direction the sun itself spins, all of them turning the same way, like a single great wheel. It is one of the most basic facts of home, so obvious we never think about it. Now imagine a world that does not. A planet circling its star backwards against the spin, moving the wrong way around a sun that turns the other. It exists. We have found it. And its very presence is a confession that something terrible once happened there. Backwards should be impossible, and for a clean reason. Remember how planets are born out of a spinning disk of gas and dust. That disk turns in one direction, and everything that condenses from it, every planet, inherits the same spin and the same direction of travel. A world born in the disk cannot come out orbiting against it, any more than a leaf caught in a river can drift upstream. So a backwards planet did not form backwards. Something turned it around after the fact. The first one we caught was WASP 17b, announced in 2009, a puffy giant more than 1,000 light years away in the constellation Scorpius. When astronomers measured the way it crossed its star, the answer made no sense at first. The planet was orbiting retrograde, moving backwards relative to its star's rotation. It was the first world we had ever found circling the wrong way. And it would not be the last, because once we knew how to look, we began finding tilted, twisted, and reversed orbits all over the place. The trick that reveals it is beautiful, and it carries a mouthful of a name, the Rossiter-McLaughlin effect. A spinning star has one edge turning toward us and one turning away. As a planet crosses the face of that star, it blocks first one edge, then the other, and the tiny shifts in the starlight betray the angle of the planet's path. Line it up, and you can tell whether the world is orbiting along the star's spin, across it, or dead against it. We can read the tilt of an orbit 1,000 light years away. And what that tilt tells us is a kind of history. A planet on a smooth, aligned orbit, moving with its star's spin, probably lived a quiet life, forming in the disk and staying more or less where it began. But a planet that is tilted sideways or flipped completely backwards cannot have had a quiet life. Something reached in and wrenched it off its original path, tipped it over, spun it around. The orbit is not just a fact. It is a record of an assault. This is why I think of these systems as crime scenes, and I mean it quite literally. An astronomer arriving at a tilted, backwards, or wildly stretched orbit is like a detective walking into a room after the violence is over. The body is still there. The furniture is overturned. You cannot watch the crime happen. It finished millions of years ago, but you can read the evidence and reconstruct what must have occurred. Every strange orbit is a frozen scene, waiting to be pieced back together from the wreckage left behind. There are a few ways to commit this particular crime. The first is brute force. In a young system with more than one giant, the planets can stray too close and fling each other around with their gravity, like a violent game of pool. One world is hurled inward, another outward, and the survivors are left on steep, tilted, chaotic orbits, knocked clean out of the tidy plane they were born in. Scattering does not politely rearrange a system. It shatters it and leaves the pieces wherever they land. The second way is slower and, in its own way, crueler. If a star has a distant companion, another star or a far-off giant, that companion's gravity can slowly torture the orbit of an inner planet over millions of years. In a rhythm called the Kozai-Lidov cycle, the planet's orbit tips further and further over and stretches longer and longer, trading its gentle circular path for something steep and violent. It is not a single blow. It is a long, patient bending until the orbit is unrecognizable. Put those together, and you get one of the leading theories for how hot Jupiters arrive in the first place. A giant, born far out, has its orbit stretched by scattering or by a distant companion until it swings in dangerously close to its star at one end. On each close pass, the star's tides tug at it, bleeding away energy, slowly shrinking and rounding the orbit until the planet is parked close in, often tilted or backwards. It is a violent road to a hot Jupiter, and the tilt is the scar it never loses. To see how brutal an orbit can get, consider HD 80606b, a giant with one of the most extreme paths ever found. It does not circle its star. It falls at it. For most of its year, it drifts far out in the cold, and then it plunges inward on a wildly stretched orbit, whipping around its star at close range before flinging back out again. Its orbit is so lopsided it looks less like a planet's than a comet's, and that plunge does something horrifying to the world. Each time HD 80606b dives past its star, it is flash heated in a matter of hours. Its temperature can rocket from something almost temperate to well over 1,000 degrees in less than a day, as the star's fury slams into it at closest approach. The atmosphere heaves. Storms of unimaginable violence erupt as the heat tries to spread. Then the planet swings back out into the cold, cools down, and waits until the next plunge does it all over again. A world that is scalded on a schedule forever. What all these worlds share is that their orbits are fossils. You cannot dig up the collision that scattered them, or watch the companion that slowly tipped them over. That drama is finished, buried in deep time. But the shape of the orbit preserves it, the way a fossil preserves the shape of a thing long dead. A backwards planet, a sideways planet, a planet on a cometary plunge, each is a bone left in the rock, a record of a catastrophe we arrived far too late to witness. And this is not some rare pathology. When astronomers went back and measured the tilts of hot Jupiter after hot Jupiter, they found that a startling number of them are misaligned, orbiting at odd angles, some sideways, some fully reversed. What looked at first like a freak, WASP-17b, turned out to be a whole population of the walking wounded. A large share of these close-in giants carry the signature of past violence in the angle of their paths. The galaxy, it seems, is full of survivors of fights we never saw. It paints a grim picture of what a young planetary system is really like. Not a nursery, a brawl. Worlds forming and then turning on each other, flinging one another into the fire or the dark, bending and breaking each other's orbits over the long, slow ages. Most of the systems we see are the ones that eventually calm down, but they calm down scarred. The tilts and the stretches and the backward orbits are the limp they walked away with. Peace out there is almost always hard-won. Which brings the mirror back around, as it now always does. Look again at our own solar system. Every planet gliding in the same direction, in nearly the same flat plane, on nearly circular paths. No backwards worlds. No cometary plunges among the planets. No obvious scars. In a galaxy full of crime scenes, our system looks less like a survivor of a brawl and more like a house where the fight, somehow, never came. That is not normal. And by now, it is not normal. There is a melancholy in being a detective who always arrives too late, and I feel it in these worlds. We can stand at the edge of a shattered system, read the angles, and know that once, long ago, there was chaos here, worlds thrown and orbits broken, and something ended violently. But we will never see it. It happened before there was anyone to watch, and it will never happen again in quite that way. We are left holding only the aftermath, reconstructing the storm from the wreckage on the shore. And here is a detail that lingers. In many of these crime scenes, we cannot even find the culprit. The companion star that tilted the orbit may be too faint to see, or long since departed. The other giant that did the scattering may have been the one flung out into the dark, gone forever. So we are left with the victim and the evidence, but no perpetrator in the room. Somewhere out there drift the guilty parties, the worlds and stars that did the throwing, scattered to who knows where. The galaxy hides its criminals well. But a broken orbit, for all its violence, means the world survived. It was thrown and it lived. Not every planet is so lucky, because the ultimate crime is not to be scattered or tilted or flung aside. It is to be devoured. And we have now caught stars in the very act of eating their own planets, worlds spiraling inward on a slow, doomed plunge toward the fire, their atmospheres being stripped and stretched toward the thing that made them. We have been watching a planet die, in real time. About 1,400 light-years away, in the constellation Auriga, there is a planet that is being eaten alive. It is a giant, larger than Jupiter, and it orbits its star so closely that the star's gravity is quite literally pulling it apart. The world has been stretched out of round, drawn into the shape of an egg, its atmosphere bleeding off the end nearest the star and streaming away toward the very thing that is killing it. It has perhaps a few million years left, and then it will be gone. We call it WASP-12b, and when it was found in 2008, it looked like just another hot Jupiter, one more giant circling too close. But this one circles closer than almost any other, a full year lasting barely a single Earth day. At that range, the star does not merely heat the planet, it grips it. The near side of the world is pulled so much harder than the far side that the whole planet is deformed, distended, a giant squeeze like clay in an invisible fist. Picture the shape of it, because it is genuinely grotesque. Not a sphere, the way we imagine a planet, but an egg or a teardrop, the pointed and straining toward the star. The tidal forces are so severe that the planet's own gravity can barely hold its outer layers down on the side facing the fire. Material at that stretch tip is only loosely bound, teetering at the edge of the planet's grasp, ready to be taken. And the star is more than happy to take it. So the star takes it. Gas is peeling off the swollen, pointed end of WASP-12b, lifted away from the planet and drawn toward its killer. Astronomers watching the system have found the world wrapped in an enormous, bloated cloud of escaping atmosphere, and beyond that, a faint stream of stolen material spiraling in toward the star. The planet is not simply losing its air. It is feeding it slowly into the furnace that is consuming it. A world giving itself up one breath at a time. And it gets worse because the planet is also falling. By timing its transits with great care over many years, astronomers have measured something extraordinary. WASP-12b's orbit is shrinking. Each year it crosses its star a fraction of a second early, because each year it has spiraled a little closer in. The world is not holding steady at the edge of the fire. It is sinking toward it on a slow, measured, unstoppable descent. We can watch the clock of its doom tick, transit by transit. How long does it have? On the order of a few million years, the astronomers estimate, before the orbit decays entirely and the planet is torn apart and swallowed. A few million years sounds like forever, but against the billions of years these worlds usually live, it is the final breath. WASP-12b is a terminal patient. We happen to have found it near the very end of its life, close enough to watch it come undone, though the ending itself will not arrive until long after our species is gone. There is no drama to it from the planet's point of view, if a planet had a point of view. No explosión, no scream. Just the slow, relentless stretching, the outer atmosphere lifting away, the ground, if there were ground, sinking imperceptibly closer to the fire year after year after year. It is death by tide and heat, on a timescale no mind could ever feel. The most violent thing that can happen to a world, drawn out so slowly that from any single moment, it looks almost still. WASP 12b shows us the long dying, but it is still only dying, still falling, its end held forever, just out of reach on the far side of deep time. For a long while, that was as close as we could get to a planet's death. We could find the doomed and the disintegrating worlds clearly on their way out, but we had never actually caught the final instant, the moment a star closes over a world and it ceases to exist. Until one night we did. In 2023, a team, led by the astronomer Kishale, announced something no one had ever seen before. Combing through data from a sky survey called ZEF, hunting for stars that suddenly brighten, they had found a strange, brief flare from a sun-like star toward the constellation Aquila. It flashed modestly and faded, but the pattern of that flash and a telltale glow of infrared light that followed it told a story that stopped the field cold. The star had just swallowed a planet. Here is what the light revealed. A giant planet, roughly the size of Jupiter, had spiraled all the way down to its star and plunged in. As it struck the star's outer layers, friction and heat flung out a burst of light, the optical flare they caught. And the plunge threw off a shroud of cooler dust and gas, which glowed in the infrared as it drifted away, the smoke from the swallowing. From 12,000 light years off, we had watched a world take its final plunge into the fire that made it. Reconstruct the scene, and it is almost unbearably vivid. For billions of years, the planet had circled its star, close and hot, its orbit slowly decaying, exactly as WASP 12b's is decaying now. Then it reached the edge. On its final orbit, it grazed the star's surface, then sank in, its atmosphere shredding, its body plunging into a fire millions of degrees hot. In hours, perhaps less, the entire world was gone, mixed into the star, its atoms now indistinguishable from the sun that ate it. A whole planet erased. We had theorized this ending for decades. We knew, in principle, that planets fall into their stars, that orbits decay, that suns devour their young. But knowing a thing and watching it are not the same. For the first time, we did not have to imagine it or infer it from wreckage. We saw the flash. We caught the death itself, in the act, in real time, across 12,000 light years of empty space. The universe let us watch a world end. And that changes something in how you have to think about these worlds. Up to now, a planet has felt like a permanent thing, a fixture, something that simply is. This chapter takes that away. Planets are born and planets die. They can be stretched apart, bled dry, and swallowed whole. They have lifespans and endings and graves. In a galaxy of billions upon billions of worlds, some fraction of them are, at this very moment, in the process of dying. Mortality, it turns out, is not just for the living. You already know where this is going, because the mirror never lets us look away for long. Our own sun will do this. In some 5 billion years, it will swell into a red giant, ballooning outward, and as it grows, it will reach for its inner children. Mercury will go first, swallowed without ceremony. Then Venus. And the Earth, this Earth, may follow them into the fire, or at best be left a scorched cinder circling a dying star. The engulfment we watch from afar is a preview of our own final act. I said this chapter's feeling was grief, and I meant it, even though it is a strange thing to grieve. These worlds are not alive. They cannot suffer, cannot fear, cannot know they're dying. And yet there is something in the death of a planet that catches in the throat. A thing that existed for billions of years, that had mountains or storms or oceans of lava. That was a place simply stops being. No one mourns it. No one even knew most of them were there. It ends, vast and voiceless in the dark. Maybe what I am really grieving is the reminder built into it. If a world that endured for 4 billion years can be swallowed in an afternoon and forgotten, then permanence is a story we tell ourselves. Everything out there is on a clock, the planets and the stars, and though we rarely say it aloud, us. The engulfments are just the universe being honest about it. Nothing is forever, not even the ground under a world's feet. Especially not that. And these deaths leave traces we're only now learning to read. Around countless stars, if you look closely, you find the chemical ghosts of worlds that fell in long ago, metals dredged up from swallowed planets, staining the light of the suns that ate them. The galaxy is quietly littered with the evidence of digestion, stars that have consumed their own worlds and carry the residue in their atmospheres. We will come back to those stained stars later, at the very end of things, when we visit the graveyards. But being swallowed, for all its finality, is at least a quick death. There is a slower one, and in some ways it is far harder to watch. Because out there is a world that is not falling into its star, but simply coming apart, disintegrating grain by grain as we look at it, boiling away into space and trailing behind a long, glittering tail of its own vaporized body. Every time it passes its star, there's a little less of it than there was before. We are watching a planet die by the grain, in slow motion across human lifetimes. There's a planet that is coming apart as we watch it, not falling into its star, not being swallowed, but simply crumbling, boiling off into space, shedding itself into a long trailing plume of dust that streams out behind it like the tail of a comet. It is a rocky world, and it is evaporating. Every time it circles its star, a little more of it is gone, carried off into the dark. We are watching a planet die, not in an instant, but grain by grain, across the span of human lifetimes. Its name is Kepler 1520b, and it began as a puzzle nobody could solve. It orbits a distant star with brutal speed, a full year lasting under 16 hours, so close to the fire that its surface smolders at 2,000 degrees. It is small, probably no bigger than Mercury, perhaps smaller, a modest rocky world of no great distinction. Except that when Kepler watched it cross its star, the shadow it cast refused to behave. And that misbehavior turned out to be the fingerprint of a world in the act of dying. Here is what was so strange. A normal planet blocks the same amount of starlight every time it crosses a clean, repeatable dip, the same shadow on every orbit. Kepler 1520b did not. One transit, it would block a good deal of light. The next, almost none. Sometimes its shadow was deep. Sometimes it nearly vanished, changing from one orbit to the next with no rhythm anyone could pin down. It was as if the planet were a different size every time it passed, which in a sense it was. In 2012, an astronomer named Saul Rappaport and his colleagues worked out what was happening, and the answer was gorgeous and grim in equal measure. The thing crossing the star was not just the planet. It was the planet plus an enormous, shifting cloud of dust streaming off it, a tail. And the size of that cloud changed from orbit to orbit, sometimes thick and light-blocking, sometimes thin. What Kepler had been watching flicker was not a solid world at all. It was the smoke coming off a dying one. The physics of why is almost cruel in its simplicity. Kepler 1520b is small, and small worlds have weak gravity. It is also blisteringly hot, close enough to its star that its dayside surface is literally vaporizing, rock turning to gas, and rising off the ground. On a larger world, gravity would pull that vapor back down. But this planet is too small to hold on. The vaporized rock escapes, rises into space, and streams away, dragging the planet's substance with it. It is too little to keep itself. So the world exhales a wind made of its own body. Hot rock vapor pours off the molten dayside, expanding out into space, and as it rises and cools, minerals condense out of it into tiny grains of dust, the way soot forms in a flame. That dust is swept back by the pressure of starlight and the planet's own motion into a long, curving tail. The planet is smoking. It is a rocky world with a chimney for a surface, venting itself into the void, one plume at a time. And here is a detail that genuinely thrills me. The dust in that tail is the planet, its interior turned inside out, its minerals lofted into space where we can, in principle, read them. By studying the light passing through the tail, astronomers can begin to work out what the world is actually made of, what kind of rock, what minerals, the very composition of its guts. It is a grim way to learn a planet's insides. We are reading its autopsy while it is still barely alive. The numbers on how fast it is dying are staggering in a quiet way. Kepler 1520b is thought to be shedding something on the order of a mountain's worth of mass with every passing orbit, venting its substance into that tail hour after hour, year after year. It is not a trickle. It is a hemorrhage, slow only by the standards of geology. Weighed against the planet's whole mass, it will take ages, but the loss is relentless, and it never pauses, and it never reverses. The world only ever grows smaller. Do the arithmetic, and you get its remaining lifespan, which is short by cosmic reckoning. Somewhere between tens and hundreds of millions of years from now, Kepler 1520b will have boiled away entirely, its last grains scattered into space, nothing left but the ghost of an orbit. On the scale of a universe 13 billion years old and counting, that is the blink of an eye. We did not just find a dying world. We found one already near the end, one that will not outlast even the span of time the dinosaurs once had. What moves me most is that we are watching it in something close to real time. Because the dust cloud changes with every orbit, no two transits of Kepler 1520b are ever quite the same. Astronomers can watch, month by month, as the tail thickens and thins, as the world has a better day or a worse one. It is the closest thing we have to a live feed of a planet's death. Not a fossil, not an inference. A world coming apart, on camera, orbit after orbit while we watch. Stand on it. In the impossible way, we keep standing on these worlds, and the dayside would be a nightmare of slow erosion. A landscape of glowing, half-molten rock beneath a swollen star, and everywhere the ground, giving up its substance to the sky, shimmering columns of vapor rising off the surface and streaming away overhead. You would be standing on a world evaporating beneath your feet, the very rock turning to smoke and leaving. There is no more literal image of impermanence than a planet you could watch dissolve. Kepler 1520b is not alone in its slow suicide. We have found a small handful of these disintegrating worlds now, each trailing its own dusty tail. One of them, called K222b, trails not one tail but two, a plume streaming ahead of it and another behind, as though the world could not decide how to fall apart. They are a rare and doomed little family. These crumbling planets, all small, all too close to their stars, all in the process of writing their own endings across the sky in dust. For all their sadness, these worlds are a strange gift to science. We almost never get to see inside a rocky planet. The interesting parts are buried under crust and cloud, sealed away forever. But a disintegrating world hands us its insides freely, vaporized and lofted into a tale we can study from across the galaxy. In dying, Kepler 1520b tells us things a healthy planet never would. It is teaching us what small rocky worlds are made of, and it is paying for the lesson with its life. There is a particular quality to this kind of death that is hard to shake. The engulfments were fast and violent, over in hours. This is the opposite. This is decay, slow and patient and utterly without drama. A world simply losing itself into the dark a little at a time. And it will go on losing itself long after everyone who ever noticed it is gone. It is the melancholy of watching something dissolve too slowly to save and too surely to deny. You cannot look away, and you cannot help. And of course the mirror is here too, because it is always here now. Every rocky world erodes, given the wrong star and enough time. Even the Earth loses a faint wisp of its atmosphere to space each day, a slow leak we never feel. We are not disintegrating like Kepler 1520b, not remotely, shielded by our distance and our gravity and our gentle Sunday. But the difference is one of degree, not of kind. Given a closer star, our world too would smoke and thin and go. We are safe only by circumstance. I keep thinking about the timescale because it is the thing that makes these worlds bearable and unbearable at once. A human life is far too short to see Kepler 1520 be visibly shrink. Generations of astronomers will watch it, and it will still be there, still crumbling, still trailing its patient tail. Our great-grandchildren, if we have them, could point their instruments at the same dying world and find it a little smaller. There is something almost tender in that, a death slow enough to be inherited, passed from one set of watchers to the next. What all of this leaves me with is a new respect for how fragile a small world can be. We think of planets as the sturdiest things there are, the very ground beneath everything. But a rocky world too close to its star is barely holding itself together, its gravity locked in a losing argument with the heat. The line between a solid planet and a plume of dust is thinner than we ever imagined. Size and distance are all that stand between a world and its own evaporation. Which brings us to the very edge of the ladder of fire, the last rung before the cold. Because there are worlds even more extreme than the crumbling ones, worlds so close to their stars that a single year passes in less time than a night's sleep, for hours, sometimes less. They graze the surface of the inferno, held together only barely against tides that strain to tear them into rubble. This is as close to a star as a planet can get, and still be a planet. Take one more step inward, and there is nothing left but to fall. There's a class of world where the very idea of a year collapses into something you could sleep through. Not a year of months, or weeks, or even days. A year of hours. On the most extreme of them, a single complete orbit around the star, one full trip that is the planet's entire year, takes a little over 4 hours. Lie down for a full night's rest, and the planet will have lived out 2 of its years before you wake. These are the innermost worlds, grazing the edge of the fire, and they should not be able to exist. To orbit that fast, a planet has to be almost impossibly close to its star, skimming just above the surface of the inferno. Its star does not hang in its sky, so much as fill it, a wall of blinding fire stretching from horizon to horizon, close enough to touch. The heat is beyond anything we have described, the surface a churning sea of molten rock, and the planet is moving at a ferocious speed, hundreds of thousands of miles an hour, because it must or it would fall. This is a world running for its life around a furnace. The record holder for a long time was a world with the unlovely name KOI 1843.03, found in the Kepler data. Its year is about 4¼ hours, one of the shortest orbits ever measured for a planet. It is small and rocky, and it circles so close to its star that the numbers, at first glance, simply do not add up. By the ordinary rules, a rocky world that close should not survive at all. It should be pulled apart. The fact that it is still there tells us something specific and slightly alarming about what it must be made of. To understand the danger, you need one idea, the Roche limit. Every star has an invisible boundary around it, a distance inside which its tides grow so ferocious they will rip apart any object held together only by its own gravity. Stray inside that line, and the star's pull on your near side so overwhelms the pull on your far side that you are stretched and stretched until you come apart into a ring of rubble. It is where moons die and comets shatter, and these 4-hour worlds orbit right up against it. So how does KOI 1843.03 survive, sitting almost on top of that lethal line? The only answer that works is that it must be extraordinarily dense, made largely of iron, a heavy metal core with little or no rock around it. A denser world has stronger self-gravity for its size and can hold itself together closer and deeper inside the danger zone. In other words, we can deduce what this planet is made of purely from the fact that it has not yet been destroyed. It is iron, because anything softer would already be gone. But surviving is not the same as being safe. A world balance that close to the Roche limit lives under constant strain, its own gravity locked in a permanent tug of war with the star, trying to tear it apart. It is likely deformed, pulled into an egg, its molten surface heaved up toward the star. Every moment is a standoff between the force holding the planet together and the force straining to pull it into a stream of debris. It exists in a state of perpetual, barely resolved crisis. The brink is not somewhere it visits. It is where it lives. Like every world this close, it is tidally locked, one hemisphere pinned forever toward the fire. That day side is not merely hot. It is almost certainly a lake of magma, glowing, churning, directly beneath a star that swallows the sky. The night side, turn away, might cool just enough for rock to freeze, a bizarre frontier of solid ground on a world whose other half is liquid. Between them, along the terminator, molten rock would meet frozen rock in a permanent, silent seam. Two irreconcilable worlds, sharing one planet, 4 hours to a year. There are others on this final rung, each terrible in its own way. Kepler 78b races around its star in about 8.5 hours. An Earth-sized world with a dayside hot enough to be a glowing ocean of lava, a genuine molten twin of our planet's eyes roasting at the very edge. When it was found, it posed a real puzzle, because by the theories of the time, there was no clean way for a world that size to have reached that close without being destroyed on the way. And yet, there it burns. Then there is GJ 367b, a world smaller than Earth, discovered circling its star in under 8 hours. Measure its density, and, like KOI 1843, it comes back extraordinarily high, an iron-rich world, likely a naked metal core with barely any rock to speak of. It is roughly the size of Mars, but built like the heart of a much larger planet, dense and heavy and scorched. These are not soft, complete worlds. They are hard, dense survivors, the kind of planet that can endure a place nothing softer ever could. These ultra-short period worlds are not freaks the way a backwards planet is a freak. Around perhaps 1 in 200 sun-like stars, there is a small rocky world whipping around in under a day, a whole quiet population of them scattered through the galaxy. They are common enough to be a category, rare enough that their origin is still argued over. Whatever process makes them, it happens again and again, all over the sky, worlds delivered right to the doorstep of destruction and somehow left to burn there. Which raises the question of what they actually are, and one idea is haunting. Some of these dense, iron-rich, ultra-close worlds may be the stripped cores of what were once much larger planets, the exposed hearts of former giants or mini-Neptunes that migrated inward and had everything else boiled and blasted away. The gas, the rock, the outer layers, all of it torn off by the star over eons, leaving only the dense metal core, too tough to destroy, circling on where a whole world used to be. A planet reduced to its own skeleton. Try to picture the view on the night side where you might briefly survive the thought of it. The sky would be black on the side facing away, but along one horizon, a permanent, furious glow, the light of the star wrapping around the edge of the world. And everything moving fast. The planet tears along its orbit so quickly that if there were fixed stars to see, they would visibly wheel overhead. A year in 4 hours means the entire sky turns, over and over, faster than the hour hand of clock. Time itself feels wrong here. This is the innermost edge of everything, the last place a planet can be and remain a planet. We have climbed the whole ladder of fire to get here, from the lava worlds to the iron rain to the crumbling planets. And this is the top rung, the closest orbit, the hottest survivable place, the very lip of the Roche limit. There is no world closer. There cannot be. Anything nearer is either falling into the star or already torn into a ring of glowing rubble. We are standing at the absolute brink of fire. And from the brink, there are only two directions, and both are down. A world here can lose its balance inward, spiral across the Roche limit, and be ripped apart into a stream of debris that rains onto the star. Or it can hold on, dense and stubborn, circling in that impossible standoff until the star itself changes and the game in some other way. What it cannot do is stay here forever, unbothered. The very close orbit is not a stable home. It is a ledge, and everything on a ledge eventually comes off it. So we have reached the end of what heat can do to a world. From here, the story cannot go any hotter or any closer or any more extreme in the direction of fire. We have run out of Inferno, which means the only place left to go is the exact opposite direction, out, away, into the cold and the dark, where a different and quieter set of horrors has been waiting for us the whole time. The fire is behind us now. Ahead, there is only the long descent into the dark. I find these brink worlds almost unbearably tense, more than the ones already dying. A crumbling planet has accepted its fate. It is simply coming apart. But a 4-hour world is caught in the act of not falling, holding itself together by the narrowest margin, iron hard and straining, right at the edge of destruction and refusing to go over. There's a kind of terrible courage in it, if a planet could have courage. It is the held breath of the whole ladder of fire, the last note before the silence. And the mirror, quietly one more time, our own innermost world, Mercury, orbits in 88 days, close and scorched and airless, and we think of it as extreme. It is nothing next to these. Mercury sits a comfortable, luxurious distance from the sun compared to a world with a 4-hour year. Even our idea of close is gentle, is safe, is spacious. The galaxy's real edge cases make our most hostile planet look like a temperate retreat. We do not even truly know how to be extreme. But there is one thing that can happen to a world more final than falling into its star and stranger than being torn apart at the brink. Its star can die. Every sun, including these furnaces, will one day burn out, swell, collapse, and end. And when a star dies, it should take its planets with it, incinerating the near ones and casting off the rest. So what do you make of a world that is still there, calmly circling the glowing corpse of a sun that already burned out? Because we have found one, and it should not have survived. 80 light years from here, in the constellation Draco, a giant planet larger than Jupiter is circling a star that is already dead. Not dying, dead. The star it orbits is a white dwarf, the burned-out corpse of a sun that ran out of fuel, swelled into a monster, and collapsed into a cinder no bigger than the Earth. Everything close to that star should have been destroyed when it died. And yet here is this world, whole and intact, calmly orbiting the grave once every day and a half. It is a survivor of the apocalypse. To understand what it survived, you have to understand what a white dwarf is. When a star like our sun reaches the end of its life, it does not explode like the giants that make pulsars. It dies more quietly and more strangely. It sheds its outer layers into space, and what remains is the core, the naked, exhausted heart of the star, crushed down to a ball the size of a planet, but weighing nearly as much as the sun. A white dwarf is a star's ghost, and it will haunt the dark for a very long time. But the dying is the violent part, and it is what makes the survivor so remarkable. Before it collapses, a star like the sun first swells. It bloats into a red giant, ballooning outward until it is hundreds of times its old size, engulfing and incinerating any planet unlucky enough to be orbiting close. Then it heaves those bloated outer layers off into space in a glowing shell, a planetary nebula, and the exposed core settles down to cool as a white dwarf. Any world that was near the star has, by then, been swallowed, scorched, or blasted away. So think about the geometry of the catastrophe. The red giant phase reaches out, sometimes as far as the orbit of Mars or beyond, a wall of stellar fire sweeping across the inner system, destroying everything it touches. Inner worlds are engulfed. Others are cooked or thrown. When the dust settles and the corpse is all that remains, there should be nothing left anywhere near it. A clean, sterilized ruin with the ember of the dead star sitting alone at the center. That is what we expect to find around a white dwarf. Emptiness. Which is why WD 1856 plus 534b stopped astronomers in their tracks when they found it in 2020. Here was a giant planet, roughly the size of Jupiter, transiting a white dwarf, crossing its face every day and a half, close in where the red giant should have obliterated it. It was the first intact giant planet ever found orbiting a stellar corpse. Not shredded remains, not a cloud of debris, but a whole world, unmistakably a planet, circling something that had already died and taken its entire system down with it. And its orbit is the deepest part of the mystery. WD 1856 plus 534b circles its dead star closer and in the star's own bloated red giant surface once reached. In other words, the planet is orbiting inside the space the star used to fill when it was dying. If the world had been on that orbit during the red giant phase, it would have been swallowed whole. So it cannot have been there then. Somehow, after the star died and shrank, this giant arrived at an orbit that should have been impossible to occupy. The question is how. The leading idea is migration, again, but of a darker kind. The planet probably survived the star's death out at a safe distance, far from the red giant's reach. Then, in a long aftermath, something pulled it inward, perhaps the gravity of other surviving worlds or a distant companion, flinging it down onto a tight new orbit around the corpse. It is a survivor twice over, first outliving its star's death, then falling inward to circle the ashes. A world that endured the end of its solar system, and then came home to the grave. Picture the scene, because it is one of the most desolate and beautiful in this whole story. A vast, dark giant, larger than Jupiter, sweeping around a tiny, brilliant point of light. The white dwarf, an object the size of the Earth but blazing with the leftover heat of a dead star. No real warmth reaches the planet from that ember. It orbits a pinprick in an endless dark, the last light of the sun that is already gone, going through the motions of a year around a star that no longer truly lives. That ember it circles is one of the strangest objects in the universe in its own right. A white dwarf packs most of a star's mass into a sphere the size of a planet, so dense that a spoonful of its material would weigh tons. It no longer burns. There is no fusion left. It simply glows with stored heat, radiating it away with agonizing slowness over billions upon billions of years, cooling toward a final darkness so distant that the universe is not yet old enough for any white dwarf to have reached it. The corpse cools but does not vanish. WD 1856 plus 534b is the rare intact survivor. But most planetary systems do not survive their star's death so cleanly, and the white dwarfs bear the evidence. Look closely at the light of these dead stars, and you find something that should not be there. Metals, calcium, iron, magnesium, the very stuff of rocky planets, sitting in the atmospheres of countless white dwarfs where by rights they should not be. And that pollution is telling us a grim story about what happened to the worlds these stars once had. Here is why the metals are a mystery and then a horror. A white dwarf's gravity is so ferocious that heavy elements should sink out of sight within days, dragged down below the surface where we could never see them. So any metal we detect in a white dwarf's atmosphere cannot be old. It must have arrived recently. It must still be arriving now, freshly falling onto the stars we watch. Something is dropping rock and metal onto these corpses continuously, and the only thing that fits is the shredded remains of their own planets. So the pollution becomes a kind of forensic evidence. By reading exactly which metals stain a white dwarf, Astronomers can work out the composition of whatever is falling in, and again, the answer looks like rock, like the crust and mantle of a planet, sometimes even like the chemistry of a world that once held water. We are, in effect, performing autopsies on destroyed planets by studying the stars that are eating their corpses. The dead worlds are gone, but their ashes are still telling us what they were made of. And around some of these white dwarfs, we can actually see the graveyard itself. Rings of dust and debris, the tidally shredded remains of asteroids and planets that strayed too close to the corpse and were torn apart at its Roche limit, ground down into a glittering disk that slowly rains onto the star. These are the ruins of former solar systems, made visible, circling their dead suns. A white dwarf with a debris disk is a headstone with the rubble of its own world scattered at its base. So around these dead stars, we see the two possible endings side by side. On one hand, annihilation, the far more common fate, whole worlds cooked, shredded, and consumed, their ashes staining the corpses that killed them. On the other, survival, rare and eerie, a planet like W1856 plus 534b that somehow made it through, still circling, still whole. The graveyard is mostly full of the destroyed, but scattered through it are these few impossible survivors, and they are, in their way, the most haunting things of all. This is what a planetary system looks like at the end of time. Not the fiery drama of a supernova, but a slow, cold epilogue, a burned-out star cooling in the dark, ringed by the dust of the world it destroyed, attended perhaps by a lone survivor circling the ember. Every star you see in the night sky that is roughly like our sun is headed for exactly this. The white dwarfs are not exotic. They are the future, the quiet, inevitable destination of most of the stars in the galaxy, ours included. Because yes, this is where our sun is going. 5 billion years from now, it will swell into a red giant, devour Mercury and Venus, scorch or swallow the Earth, and then shrug off its outer layers and collapse into a white dwarf. Our sun will become one of these embers, an Earth-sized cinder cooling in the dark, orbited by whatever ruined outer worlds remain, perhaps trailing the dust of the very planet you're standing on. The graveyard we are visiting is, eventually, our own. We're looking at the tombstone with our name already half carved into it. There's an awe in the survivors that I cannot quite put down. To picture a world that watched its star die, that endured the swelling and the shedding and the collapse, and that is still there, still circling, still keeping time around the corpse, is to picture a kind of loyalty the universe never asked for and does not reward. It is magnificent, and it is unbearably lonely. A planet faithfully orbiting an ember in a graveyard of its siblings, under a sky where its sun is only a memory. The cold is almost won here. Almost. But there is another way for a world to end up alone in the dark, and it does not require its star to die at all. Some worlds are not destroyed and not left circling a corpse. They are exiled, flung by ancient violence onto enormous, tilted, barely bound orbits at the frozen edges of their systems, so far out that their star is no longer a sun at all, just another cold point of light among the countless others. Still owned by a sun they can no longer feel, cast out to the very border of belonging and the void beyond it. Imagine standing on a world where your sun is not a sun at all, where the star that owns you, that you technically orbit, that gave you whatever warmth you have, is nothing in your sky but a single bright point of light, indistinguishable at a glance from all the other stars. No disk, no warmth you could feel, just a slightly brighter pinprick in an endless field of them. There are worlds like this, cast so far out into the dark that they have all but lost their own sun. We call them the Exiles. The most famous of them is HD 106906b, a giant world some 300 light years away in the southern sky. It is enormous, around 11 times the mass of Jupiter, right at the blurry edge between a planet and a failed star. And it orbits its sun at a distance so vast it strains belief, hundreds of times farther out than the Earth is from our own sun, out on the frozen, lightless fringe of its system where almost nothing should be. Let me try to make that distance real, because the numbers are almost meaningless without a handhold. The Earth sits 1 unit from the Sun. We call it an astronomical unit. Neptune, our most distant major planet, orbits at 30. Pluto wanders out to around 40. HD 106906b orbits its star at something like 700 of those units, roughly 20 times farther out than Neptune, out in a cold so deep the star can barely be said to reach it at all. It is exiled to the very doorstep of interstellar space. Out there, the star delivers almost nothing. The light that reaches HD 106906b is a feeble ghost of sunlight, hundreds of thousands of times fainter than the sun we know, too weak to warm anything, too dim to light a landscape. This is a realm of permanent, profound cold, where any world would be frozen to its core, its surface a wilderness of ice and rock in near total darkness. The Exile is not merely far away. It is functionally abandoned, orbiting the memory of sun it can no longer feel. So how does a giant planet end up flung to the edge of the void? The story is the familiar violence, told a larger scale. HD 106906b most likely did not form out there. It is far too empty a place to build a world that big. Instead, it probably formed closer in and was then scattered, hurled outward by a gravitational encounter, a near miss with another giant or the tug of the double star at its system's heart. It was thrown toward the exit, and something, perhaps a passing star, nudged it into a wide, barely bound orbit instead of out the door entirely. And it seems to have left a mark on its home as it went. The inner system of HD 106906 is ringed by a great disk of debris, a belt of icy rubble much like the frozen ring at the edge of our own solar system. But that disk is lopsided, skewed, pulled out of shape, and the exiled giant far outside, it is the prime suspect. From its lonely orbit on the fringe, its gravity still reaches back and disturbs the ruins of the system it was cast out of. Even in exile, it haunts the place it left. The word that matters most for these worlds is bound, and only barely so. A planet this far out is held to its star by the faintest thread of gravity. It would take almost nothing to sever it, a slightly harder shove, the pull of a passing star, and the exile would slip free entirely, drifting off into interstellar space forever. HD 106906b sits right at that edge, 1 foot in its system and 1 foot in the void, belonging to its sun by the thinnest possible margin. Exile is not quite banishment, but it is close. Out at that distance, time itself stretches almost past comprehension. A single orbit, 1 year for HD 106906b, takes something like 15,000 of ours. When this planet last completed a lap around its star, human beings were painting on the walls of caves, and the Ice Age had not yet loosened its grip. It will not finish its next orbit until a future so distant we cannot picture the world that waits there. The exiles do not just live far away. They live slow, on a clock that makes all of human history a rounding error. Here is something remarkable about these worlds, though, a gift hidden inside their loneliness. We can actually see them. Almost every planet in this documentary was found indirectly by a shadow or a wobble, never glimpsed as more than a number on a chart. But the exiles orbit so far from their star's blinding glare that we can photograph them directly, capture their actual light, a faint up beside a massed-out star. HD 106906b is not an inference. It is a photograph. We have seen its face out there in the dark. The reason we can is a cruel kind of luck. These exiled giants are young, and youth, for a planet, means heat. Freshly formed, still glowing from the warmth of their own making, they shine faintly in infrared light, hot enough to be seen against the cold. And because they orbit so far from their star, that faint glow is not drowned out by its glare. So the very things that make them lonely, their distance and their exile, are what let us see them at all. We can only photograph the ones the galaxy has cast out. HD 106906b is not alone in its isolation. There's a world called GU Piscium b that orbits its star at a staggering 2,000 astronomical units, a distance so great its year lasts something like 80,000 of ours, a planet exiled almost past the meaning of the word orbit. And around a young star called HR 8799, we have directly imaged an entire family of giants strung out across the cold, a rare portrait of a whole system's distant worlds. The galaxy keeps many of these far-flung giants, drifting at the edges of the light. What defines an exile is that it lives on a border, the border between belonging to a star and belonging to no one. Come a little closer in, and a world is a proper planet, warmed and lit and held. Drift a little farther out, and it is cut loose entirely, a wanderer of interstellar space. The exiles occupy the thin, cold zone between those two states, still nominally owned by a sun, but so distant from it that the ownership is almost a technicality. They're the last world still inside the light, standing at its farthest edge. And that is the particular sorrow of the exile. If a world can carry sorrow, it still belongs. On the charts, HD 106906b is a planet of its star, listed as its possession, bound to it by gravity across all that emptiness. But it cannot feel that bond in any way that matters. No warmth, no meaningful light, no sense of sun overhead, only a distant point among the stars that it happens, technically, to circle. It is owned by something it can no longer experience. That is as close to abandonment as physics allows. Stand on a moon of HD 106906b, if it has one, and look up. The sky would be almost pure night, a deep and total darkness spread with stars. And somewhere in that field, one point would shine a little brighter than the rest, steady, cold, and small. That is your sun. That is the star that made you, that owns you, that you have orbited for 15,000 years and will orbit for 15,000 more. And you could cover it completely with the tip of one raised finger. Through this whole story, the dark has been approaching, chapter by chapter, world by world, and here on the Exiles, it has all but arrived. The lava world screamed with fire. The dying worlds at least had a sun to fall toward. But the Exile has almost nothing left of its star. Only that distant spark in the deep, patient cold. This is cosmic loneliness made into a place. A real world, enormous and ancient, adrift at the ragged edge of the light, as good as alone. And still, it has not quite crossed the final line. There is even a question of what to call them. At 11 times the mass of Jupiter, HD 106906b sits near the boundary where a planet shades into a brown dwarf, a failed star too small to ever ignite. Some of these directly imaged giants may not be planets in the ordinary sense at all, but objects that formed more like tiny stars, alone out of collapsing clouds. Out here at the edge, even our categories blur. The Exiles test not just where a planet can be, but what a planet even is. I find the Exiles the most quietly devastating worlds we have met, and it took me a while to understand why. It is not the cold, or the distance, or the slow, endless years. It is the almost. They almost have a sun. They're almost free. They belong and they do not. They are held by a thread they cannot feel, in a dark that is not quite absolute, forever on the threshold of a loneliness they have not yet fully entered. Which makes the next step, the final step, so much colder. Because some worlds have taken it. Because now take away the star entirely. Not a dying star, not a distant star, not a faint and feeble star, but no star at all. Cut the thread completely. Sever the Exile's last thin bond to its sun and let it drift free out of any system into the true dark between the stars alone. There are worlds like that. And this is the part that should stop you cold. They may be the single most common kind of world in the entire galaxy. Planets with no sun, adrift in permanent night, falling through the black forever. There's a planet falling through the dark right now, and it has no sun. It never did, or it lost the one it had long ago. It drifts alone through the empty space between the stars, in a night so complete that its own hand, if it had one, would be invisible before its face. No dawn will ever come. No season will ever turn. It simply falls silent and frozen and unseen through the black, and it has been falling for billions of years. And it may be the single most common kind of world in the galaxy. We call them rogue planets or free floating planets, and the name barely captures how strange they are. They are worlds, real planets, some rocky, some giant, that belong to no star at all. They orbit nothing. They are not in any solar system. They wander through interstellar space entirely alone, bound to nothing but the slow gravity of the galaxy itself, drifting between the stars on journeys with no destination and no end. A planet is supposed to have a sun. These do not, and there may be more of them than there are stars. Let that number land properly, because it is the heart of this chapter. When astronomers try to estimate how many of these starless worlds are out there, the counts come back staggering, easily in the billions, and by some estimates, the free floating planets may outnumber all the stars in the galaxy. Think about that. The night sky is full of stars, hundreds of billions of them, and drifting invisibly between them, unseen, maybe even more worlds with no star at all. The most common home in the galaxy might be a planet in permanent darkness. You might reasonably ask how we could possibly find a world that gives off almost no light, orbits nothing, and drifts in the dark. It sounds impossible, and it very nearly is. But there is one trick, and it is exquisite. When a rogue planet, invisible itself, happens to drift precisely in front of a distant background star, its gravity bends and briefly magnifies that star's light, making the star seem to flare up and fade over hours or days. We do not see the planet. We see its gravity betrayed by the star behind it. This is called microlensing, and it is a haunting way to find a world because it happens exactly once. The alignment is a fluke, a one-time crossing that will never repeat. The star brightens, holds, and dims, and then the rogue moves on into the dark and is lost to us forever, its position, its path gone. We catch a single fleeting shadow of its passing and nothing more. Every rogue we find this way is a world we glimpse for a moment and then never see again. A ghost confirmed and then gone. So where do they come from? Many of them, we think, are exiles who lost their last thread, the ultimate losers of the wars we watched in the early chapters. Remember the scattering, the giants flinging smaller worlds around, the gravitational slingshots that threw planets outward. Push a world hard enough, and it does not settle onto a wide orbit like the Exiles. It is thrown clean out of its system, past the point of no return, cut loose forever. Every violent young solar system may have fired off worlds like bullets into the dark. These are where they landed. But not all of them were cast out. Some, it seems, were born this way, alone from the very start. In the great clouds where stars form, not every clump of collapsing gas gathers enough mass to ignite into a star. Some fall short, condensing into planet-sized worlds that never had a sun to orbit because they formed on their own, like stars that failed to light. These rogues are not orphans. They are only children, worlds that came into being in the dark and have never known anything else. Solitude was not done to them. It is simply what they are. And the galaxy keeps surprising us about them. In 2023, the James Webb Space Telescope stared into the Orion Nebula, one of the great stellar nurseries, and found something nobody predicted. Dozens of free-floating, planet-sized worlds, many of them drifting not alone, but in pairs, two giant rogues loosely circling each other with no star anywhere in sight. We do not fully understand how such pairs can exist. They should not by our theories. But there they were, couples of sunless worlds wandering the nebula together in the dark. Try to imagine the surface of one of these worlds, and your imagination runs out of light. There is no sun, so there is no day, ever. There is no night either, Not really, because night implies a day that will return. There is only the dark, permanent, and total, unbroken since the world's beginning. The stars would be there, scattered across a black sky, cold and distant and utterly indifferent. But no dawn will ever rise over the horizon. Nothing will ever cast a shadow. It is a world where light from outside simply never comes. You would expect such a world to be frozen absolutely solid, a rock at the temperature of deep space, and its surface very nearly is hundreds of degrees below zero. But here is the twist that changes everything. A planet is not only warm from outside, it carries heat within, left over from its formation, and generated still by the slow decay of radioactive elements deep in its core. A starless world is dark and frozen on the outside, but inside, in its buried heart, it may still be warm. And that changes what is possible. Because if a rogue planet has enough internal heat and a thick enough blanket of ice above, then something almost unthinkable becomes possible. Beneath the frozen crust miles deep, warmed from below by the planet's own inner fire, there could be liquid water, an ocean, a dark, sealed, sunless sea, locked forever under ice, on a world with no star, drifting between the lights of the galaxy. We see hints of exactly this arrangement in our own solar system, on the icy moons of Jupiter and Saturn. A rogue could carry such an ocean out into the endless dark. There's more than one way for these worlds to hold their warmth. A large rogue, giant-sized, might wrap itself in a thick atmosphere of hydrogen, a blanket so effective it traps the planet's inner heat for billions of years, keeping the surface, or an ocean beneath it, from ever fully freezing. Smaller rocky rogues rely on the slow radioactive burn in their cores, the same heat that drives the volcanoes and drifting continents of our own world. In the total dark, a planet becomes its own source of warmth, or it becomes nothing at all. And so we arrive at a possibility that is either the loneliest or the most hopeful idea in this entire film, and I genuinely cannot decide which. In those sealed, sunless oceans, warmed by a world's inner heat, far from any star, life might not be impossible. On Earth, whole ecosystems thrive in the black depths of our oceans, around volcanic vents, never seeing the sun, feeding on the planet's own heat and chemistry. There is no law that says such life needs a star. Somewhere out there, in the dark between the stars, an ocean no sunlight will ever touch might not be entirely empty. Now multiply that by the numbers. If rogue planets truly outnumber the stars, then the galaxy is not, as we always pictured it, a scattering of bright suns with a few worlds each. It is something far darker and far more crowded. It is a vast, black ocean filled to overflowing with sunless worlds, most of them frozen, some of them perhaps hiding hidden seas, nearly all of them invisible to us, drifting in a night that has no end. The typical home in the galaxy is not a place like Earth. It is a wanderer in the dark. This is the darkest truth the search for other worlds has turned up, and I want to state it plainly because the whole film has been walking toward it. The most common kind of planet in the galaxy may be a world with no sun, adrift in permanent night, seen by nothing, warming no one, its oceans, if it has any, sealed forever beneath ice, falling through the black for all of time. Not a rare tragedy. The default, the ordinary outcome. Most of the worlds that exist for no one in the dark alone. There's a fear that comes with truly grasping this, and it is not the fear of fire or of dying. It is the fear of scale, of indifference, of a universe so vast and so dark that most of its worlds will never be seen, never be warmed, never matter to anyone or anything. Billions of planets, whole worlds with mountains and oceans and slow inner fires, wandering the void in total silence, having never known a sunrise and never destined to. It is sublime and it is terrible. It makes the ground beneath you feel very small and very precious. And of course, the mirror waits for us here too, at the very bottom of the dark. In the chaos of our own young solar system, when the giants were migrating and scattering, worlds were thrown. Some fraction of the Earth-sized bodies that once formed near us may have been flung out, cast into the interstellar dark to wander as rogues. It could have been us. A slightly harder shove in those violent early years, and the Earth itself might have been thrown from the sun, sent drifting into the black, its oceans freezing over, all of this, everything sealed forever under ice. We were very nearly a wanderer. We were spared by inches. This is the farthest into the dark this story goes, and I will not pretend it is a comfortable place to stand. We began with a planet that burned too bright beside its star. We are ending out here with worlds that have no star at all, falling silent and frozen through the space between the suns, most of them never to be seen by anyone. That is the shape of the galaxy, as far as we can tell. Overwhelmingly cold, overwhelmingly dark, overwhelmingly alone. And it makes what comes next feel almost unbearable to say. Because now, finally, we have to turn all the way around. We have cataloged the fire and the dark, the drowned worlds and the boiling worlds, the survivors and the exiles and the wanderers with no sun. We have seen what the galaxy actually builds over and over at enormous scale. And through all of it, one small, quiet, watery world has been sitting behind us, unremarked, keeping us alive. It is time to look at it honestly, the way we have looked at all the others. But before we do, there is one last piece of unfinished business. Because here's a thought to keep you up at night. If the galaxy is this full of monsters, this crowded with worlds we cannot see, then how sure are we, really, about our own home? How certain are we that we have found everything orbiting our own sun? There are astronomers, serious ones, who believe there is a large planet hiding in the outer darkness of our own solar system, unseen, unfound, betraying itself only by the strange way it seems to be hurting distant worlds far beyond Neptune. Even home, it turns out, may still be keeping a secret in the dark. For the last 18 chapters, we've been hunting monsters in other star systems, comfortable in the belief that our own house, at least, we know. We have counted our planets. 8 of them, mapped, measured, familiar. But there are astronomers who will tell you that count is wrong. That there is a 9th world out there, in the frozen dark far beyond Neptune, enormous and unseen, and that we can feel its gravity right now, tugging on things at the very edge of the sun's reach. We have not found it. We may be haunted by it. The story of this ghost begins not with a sighting, but with a pattern out at the very fringe of the solar system. Far past Neptune, past even Pluto, there's a population of small, icy worlds on enormous, looping orbits, the most distant things bound to our sun. And when astronomers plotted the paths of the most extreme of them, they noticed something that made no sense. The orbits were not scattered randomly, the way chance would leave them. They were lined up, clustered, all leaning the same way, as though something were holding them in formation. The strangest of these distant objects carries a name out of myth, Sedna, discovered by the astronomer Mike Brown in 2003. Sedna never comes anywhere near the known planets. Even at its closest approach to the sun, it stays far beyond Neptune, out in a lonely, detached orbit that takes 11,000 years to complete. Nothing we know of could have placed it there. It is too far out to have been flung by Neptune, too bound to have escaped entirely. Sedna is a world on an orbit that our 8 planets simply cannot explain. And Sedna is not alone in its strangeness. There's a small family of these extreme, detached worlds, and their orbits share that eerie alignment, all tilted the same way, all pointing in roughly the same direction in space, as if combed. Left to chance, orbits like these should sprawl every which way, randomly oriented. Instead, they cluster, tightly enough that astronomers put the odds of pure coincidence at less than 1 in 100. Something, it seemed, was gently herding the most distant objects in the solar system onto matching paths. In 2016, 2 astronomers at Caltech, Konstantin Batygin and Mike Brown, put forward a bold explanation. The clustering, they argued, was not random and not a fluke. It was the gravitational signature of a large, undiscovered planet, far out in the dark, whose pull was quietly shaping the orbits of everything beyond Neptune. They ran the simulations. A planet of the right mass, on the right distant orbit, reproduced the strange alignment almost perfectly. They called it Planet 9, and they went looking for it. The logic is the same logic that found Neptune itself back in the 1840s. Astronomers then noticed Uranus was being tugged off course by something unseen, calculated where the hidden culprit must be, pointed a telescope, and there was Neptune, almost exactly as predicted. A planet found by its gravity alone before anyone laid eyes on it. Battigan and Brown are making the same wager, one solar system further out. They see the tug. They have calculated the culprit. Now they, and everyone else, are hunting for the world at the end of the math. So what would Planet 9 actually be? Their best estimate is a world of roughly 5 to 10 times the mass of the Earth, out on a vast, stretched orbit hundreds of times farther from the Sun than we are. It would be a giant compared to our rocky worlds, a genuine planet, larger than Earth, smaller than Neptune. And here is the detail that makes me smile every time, given everything we have learned. That size, bigger than Earth and smaller than Neptune, is the single most common kind of planet in the entire galaxy, the super-Earth. Do you remember the great absence from the turning point of this film? The super-Earth, the galaxy's favorite world, the most common planet there is, the one type our solar system conspicuously lacks. We stood there and marveled at how strange it was that we did not have one. Well, if Battigan and Brown are right, we do. It has been here the whole time, hiding in the outer dark, the missing super-Earth, the very thing that made us an anomaly, waiting at the edge of our own system for us to find it. Our strangeness might have a secret exception. There is a delicious irony in who is leading the search. Mike Brown is, by his own cheerful admission, the man who killed Pluto. His discoveries of distant worlds like Eris, a body as large as Pluto, forced astronomers to demote Pluto from planet to dwarf, dropping our count from 9 to 8 and breaking a generation's hearts. And now the same man is arguing that there really is a 9th planet after all, a true one this time, far grander than Pluto ever was. He took 9 away. He is trying to give it back. The reason we have not simply pointed a telescope and settled it is the sheer, punishing distance. If Planet 9 exists, it takes something like 10 to 20,000 years to circle the Sun once. It is so far out that the Sun, from there, would be a merely bright star, and the planet would reflect only the faintest whisper of light back to us. It could be anywhere along that immense orbit, in any direction, a dim, slow-moving speck lost in a sky crowded with far brighter stars. We're looking for a black cat in a coal cellar, and the cellar is the size of the sky. Everything about it conspires to keep it hidden. It is dark because so little sunlight ever reaches it. It is slow, creeping across the sky so gradually that in a single night, it barely seems to move against the fixed stars. And nobody knows exactly where to look, only a broad arc of possibilities spanning a huge stretch of the heavens. Searching for it means photographing enormous swaths of sky, again and again, hunting for the one feint that shifts between the pictures. It is painstaking, and so far it has come up empty. But the net is tightening. Astronomers have been scouring the sky with powerful instruments like the Subaru telescope in Hawaii, ruling out patch after patch. And a new observatory in Chile, the Vera Rubin Observatory, is beginning a survey that will photograph the entire southern sky over and over for years, exactly the kind of deep, repeated, wide search that could catch a slow, faint mover. If Planet 9 is real and out there, this new, I may finally find it. Within a decade, we may either see the ghost or prove there was never one at all. And plenty of astronomers suspect there is no ghost to find. The strongest objection is a subtle one about how we look. We tend to discover these distant objects in the same seasons, from the same observatories, pointed at the same patches of sky. So perhaps the clustering is not real at all. but an illusion baked in by where and when we happen to be searching. Correct for that bias, the skeptics argue, and the eerie alignment might soften into ordinary randomness. The pattern that launched Planet 9 may be a trick of our own limited vantage. Even among those who take the clustering seriously, not everyone agrees it is a planet. Some have wondered whether the gravity could come from a great disk of unseen small bodies out there, rather than one large world. And a few, only half joking, floated a stranger idea still, that the hidden mass could be a small primordial black hole, left over from the birth of the universe, no larger than a grapefruit, but as heavy as a planet, lurking silently at the edge of the sun's domain. We genuinely do not know. The thing tugging on those orbits, if it is real, has not yet told us what it is. If it does turn out to be a planet, the discovery would be staggering. It would mean our solar system, the one we thought we had fully mapped, has been hiding a whole world larger than Earth for the entire span of human history, right in our own backyard, and we simply never noticed. It would rewrite the textbooks, restore our count to 9, and hand us, at last, the super-Earth the galaxy insisted we should have. A new planet, found not by luck, but by the ghost of its gravity. The last great discovery of our own solar system. But whether or not it is ever found, Planet 9 has already taught us something humbling. For all our confidence, for all our maps and probes and centuries of watching, we cannot be certain we know our own house. There may be a world out there, larger than the Earth, orbiting the same sun that warms your face, that we have never seen and cannot yet find. If a planet that big can hide in our own solar system, then our sense of having the place figured out is, at best, provisional. Even home keeps secrets in the dark. I find something fitting in ending our tour of the impossible right here on our own doorstep. We spent 18 chapters unnerved by the strangeness out there, the monsters around other stars. And now we come home to discover that home itself may be haunted, that the dark at the edge of our own system might hold one more secret we have not been allowed to see. The galaxy's habit of hiding worlds does not stop politely at the orbit of Neptune. It reaches all the way into us. Nowhere, it seems, is ever fully known. And yet, ghost or no ghost, Planet 9 is not the real mystery this film has been circling all along. Because there is one world in this entire story stranger than any we have met. Stranger than the lava seas and the iron rain. Stranger than the drowned worlds and the wanderers with no sun. It is a planet that is temperate and wet and stable and calm and alive in a galaxy that builds almost nothing of the kind. It has been beneath your feet this whole time, and it is time at last to see it for the impossible thing it is. We have traveled a long way in the dark together. We have stood beside oceans of lava and storms of iron, watched worlds boil away and stars eat their children, drifted past the exiles and the wanderers with no sun at all. And now I want you to do something simple. Look down at the floor, the ground, whatever is beneath you. Because after all the impossible worlds we have hunted across this galaxy, the strangest one of all, the true anomaly, the planet that should not exist, is the one you are standing on right now. Start with the thing you never noticed, because you have never once been without it. This world is mild. The temperature outside, right now, is almost certainly one at which water stays liquid and a human being can simply exist, unprotected, breathing freely. Think of where we have been. For 1,000 degrees, 200 below zero, iron rain and glass wind and permanent frozen night. And here, this thin band of the merely pleasant, this narrow ribbon of temperatures where a body can walk around unharmed. In a galaxy we have surveyed that is almost unheard of. Then there is the water. Not water sealed under miles of ice, not water boiled into vapor, not exotic hot ice crushed in the dark, but liquid water on the surface, in the open, in oceans and rivers and rain, and the cells of your own body. For water to pool on a planet's surface and stay there for billions of years, everything has to be right: the distance from the star, the pressure of the air, the steadiness of the warmth. We have found almost nowhere else it certainly happens. Here, it covers most of the world. And it has lasted. This is perhaps the rarest miracle of all, and the easiest to miss. The Earth has held these conditions, roughly, for close to 4 billion years. Not 4 days or 4,000 years, but 4 billion. Long enough for single cells to become fish, for fish to crawl on a land, for forests and dinosaurs and cities, and you. No engulfment, no fatal migration, no plunge into the star, no ejection into the dark. Just an almost unbroken stretch of calm, on a timescale the violent worlds of this film can barely comprehend. Stability itself is a kind of impossible luck. We have already seen why, in glimpses scattered through this story. A giant named Jupiter standing guard at the edge that may have swept the inner system clear and stopped a hot Jupiter from ever forming, or a super-Earth from crowding us out. A wide, calm, orderly architecture, planets on gentle circular paths, no backwards worlds, no cometary plunges, none of the scars that mark almost every other system we have met. The anomaly we named at the turning point of this film was not an abstraction. It was the very machinery that made a stable home possible. There are smaller graces, too, easy to overlook. That pale companion in our sky, the moon, is unusually large for a world our size, and it does something quietly vital. Its steady gravity holds the tilt of the Earth almost fixed, keeping our seasons mild and regular instead of letting the planet wobble and lurch through wild swings of climate. It was born, we think, out of a catastrophe, a colossal collision in our infancy. A disaster for billion years ago turns out to be one of the reasons the weather has been gentle enough for you to be here to feel it. Look deeper, and the good fortune keeps compounding. Beneath your feet, the planet is alive with slow fire. Its interior is still hot enough to churn, driving the drifting of continents that recycles carbon and steadies the climate across the ages. Around the whole world runs an invisible magnetic shield generated by that molten core, deflecting the worst of the sun's radiation that would otherwise strip our air away, the way it was stripped from so many worlds we have watched. None of this had to be. All of it together is why the air is still here. People like to call this the Goldilocks arrangement, everything just right, and I have always found that phrase too cozy for what it describes. Goldilocks walked into a house already built for her. Nobody built this. There was no plan, no purpose, no hand arranging the distance and the water and the giant guardian and the sheltering moon. It is not that the porridge was made to be the right temperature. It is that out of billions upon billions of worlds cooked at every wrong temperature imaginable, this one, by sheer accident, came out warm. We are not the intended guest. We are the improbable coincidence. And this is the strange inversion the whole film has been building toward. In a cabinet full of monsters, the exhibit that stops you cold is the ordinary one. A mild, blue, watery world with gentle weather and a stable orbit. The most boring postcard imaginable is, against the galaxy we have actually surveyed, the single most extraordinary object in this entire story. Its very unremarkableness is what makes it a freak. Everywhere else, the impossible is the rule. Here, the impossible thing is how completely, reliably, almost tediously livable it is. But we have saved the real anomaly for last, the one thing that truly sets this world apart from every other we have ever found. Life, not the possibility of it, not a sealed dark ocean where it might conceivably hide, but life, actual, undeniable, everywhere, teeming in the soil and the seas and the air, in numbers beyond counting, in forms beyond imagining. In 400 years of searching the sky, across thousands of worlds, we have found exactly one planet where matter woke up and started to look around. You're living on it. You're made of it. And on this one world, out of all of them, something happened that may be rarer still. The life here got up off the ground and looked up and began to wonder. Somewhere in the last few thousand years, a species of clever, frightened animals started building instruments to measure the wobble of distant stars and worked out that the galaxy is full of worlds and named them and asked whether any of them were like home. This entire film, every impossible planet in it, exists because one anomalous world grew something that could ask the question. The universe, here, open an eye. Now hold all of that and feel how thin it is. The air that keeps you alive is a film, a skin, a few miles of gas so shallow that on a globe it would be thinner than a shine on an apple. The temperate band we live in is narrow, and the balance that holds it is delicate, easily pushed. This is not a fortress. It is a soap bubble, a rare and gorgeous accident of chemistry and distance and time, holding back an entire galaxy of fire and ice and dark. And we are all of us inside it. And as far as we can tell, we are inside it alone. We have listened and heard nothing. We have searched thousands of worlds and found no other voice, no other city, no other eye looking back. Maybe they are out there and we have simply not found them yet. Maybe the sealed oceans of the wanderers hold life that will never know we existed. But right now, tonight, this is the only world we know of where anyone is home. One planet, in a galaxy of hundreds of billions, where the lights are on. There's a weight to that silence I do not think we let ourselves feel very often. The galaxy is crowded with worlds and empty of company. All those planets, all that real estate, the drowned and the boiling and the frozen and the dark, and not one of them, so far, has answered. It may be that living worlds are so rare that whole galaxies hold only a handful. It may be that we are, for all practical purposes, the only ones who will ever know this particular story was told, that is either unbearably lonely or unbearably precious. Perhaps it is both. So this is what the search for other worlds has really given us in the end. We went looking outward, hoping to find ourselves reflected in the stars, other Earths, other cradles, cousins in the dark. And instead, the galaxy handed us 400 years of monsters and taught us, slowly, that the thing we were looking for was the thing we were standing on. We did not find home out there. We found out how strange home is, how rare, how very nearly impossible. And here is the part one cannot let you leave without, because it is the whole point. This rare, improbable, impossible world is fragile, and it is the only one we have, and we are not treating it that way. We are the single anomaly in a galaxy of dead ends, the one place the universe woke up, and we are busy thinning the very air and warming the very balance that let us exist at all. Knowing what is out there, knowing how the galaxy usually turns out, that is not an abstract fact. It is the most urgent argument imaginable for taking care of the one exception. But I do not want to leave you only in dread, because there is wonder here too, and it is the same size as the fear. You are alive, right now, on the strangest planet in this entire film, the one that should not exist and somehow does. You get to see the sky. You get to feel the warmth of a star at exactly the right distance, and drink liquid water and love other conscious creatures on a world where, against every odd the galaxy could throw, matter learned to wonder about itself. That is not a small thing. It may be the rarest thing there is. I have spent this whole film in the dark with you, finding a grim kind of wonder in worlds that would kill us without noticing. And every one of them, in the end, was only ever a way of pointing back here. The lava seas and the iron storms and the sunless wanderers were the frame. This quiet blue world was always the picture. I did not tell you about the planets that should not exist to frighten you about the galaxy. I told you so that when you walk outside tonight, you might for one moment see this place the way it actually is. So do that if you can. Go outside. Look up at the same stars we have been traveling between, and understand that around nearly every one of them turn worlds of fire and ice and dark, silent and hostile and empty. Then look back down at the ground, at your own hands, at the impossible, warm, wet, living world that made them. In 1990, we turned a departing spacecraft around and photographed the Earth from 4 billion miles away, and it was almost nothing, a single pale blue dot a mote of dust caught in a sunbeam. Everyone who ever lived is on that dot. Everything you have ever known. In a cosmos overflowing with worlds that should not exist, drowned worlds and boiling worlds, backwards worlds and crumbling worlds, worlds circling corpses and worlds circling nothing at all, there's exactly one that truly should not. It is temperate and wet and stable and rare beyond all reckoning, and it is keeping you alive at this very moment. It is fragile. It is, as far as we can tell, alone. And it is the only home, the only life we have ever found has ever had. Take care of the planet that should not exist. There does not appear to be another.